What if the universe held worlds more terrifying than any nightmare? Imagine a planet where diamonds rain from the sky, glittering with dangerous beauty, or the Inferno realm plagued by relentless firestorms where survival is impossible. There's an ice giant that unleashes violent hailstorms of methane, while another world swathes itself in clouds of sulfuric acid, corrosive and toxic. A tidal locked planet bakes under extreme heat, while supervolcanic eruptions continually reshape another's surface. Prepare to confront a frozen world with dark, swirling storms and an ocean planet that harbors crushing depths, ready to engulf all. Let's explore some of the most horrifying planets where life, as we know it, cannot exist. The planet known for diamond rain is called Neptune. Situated in our solar system, Neptune is the 8th planet from the Sun. This distant gas giant, with its striking blue color caused by methane in its atmosphere, has conditions that sometimes create extraordinary phenomena. As scientists delve into Neptune's atmosphere, they believe that the immense pressures and temperatures deep within the planet can turn carbon into diamonds. Imagine the extreme conditions similar to those created in a diamond pressure cooker. Under such intense pressure, carbon atoms can bond together in a crystalline structure, forming diamonds. These diamonds are thought to form high in the atmosphere, where they are speculated to fall like raindrops towards the planet's core. This captivating process highlights the complexities of planetary atmospheres and the potential for bizarre weather that exists in the far reaches of our solar system. On planets like Saturn and Jupiter, scientists theorize that conditions exist where diamond rain might form due to extreme pressure and temperature deep within their atmospheres. These gas giants have thick atmospheres primarily composed of hydrogen and helium, but they also contain significant amounts of carbon. In the upper atmosphere, carbon exists in gas form, but as you descend deeper, the pressure increases dramatically. Imagine descending into a deep ocean. As you go lower, the pressure becomes more intense. At certain depths on these gas giants, the pressure can become so high that it compresses carbon into solid form. This process transforms carbon into a dense structure resembling diamond crystals. When conditions are just right, where pressure and temperature align, the tiny diamond particles begin to coalesce and precipitate, similar to how rain forms in a cloud. Once these diamond particles are formed, they may actually fall through the atmosphere, making their way toward the core of the planet. As they descend, they could create a shimmering spectacle, akin to raindrops falling from above, albeit made up of precious gemstones rather than water. This fascinating concept shows how extreme environmental conditions can lead to the creation of materials that, under ordinary circumstances, are found only on Earth's surface. Scientists study these processes through both laboratory experiments, simulating high-pressure environments, and by analyzing the spectral data obtained from space probes, piecing together the mysterious story of diamond rain among the giants of our solar system. The phenomenon of diamond rain is a fascinating occurrence that takes place under extreme conditions found in certain planets and moons, particularly in our solar system. To understand how diamonds can form or precipitate as rain, we need to consider the right environment and the right elements. Firstly, the essential ingredient for diamonds is carbon. On Earth, carbon atoms bond under high pressure and temperature to create the crystalline structure of a diamond. However, in the environments of some gas giants, like Jupiter and Saturn, the conditions are drastically different yet ripe for this transformation. In these massive planets, the atmosphere is predominantly made up of hydrogen and helium, but also contains trace amounts of hydrocarbons, which are compounds made of hydrogen and carbon. The extreme pressures deep within these planets can exceed what we find in the most crushing depths of Earth's geology. When lightning bolts or other forms of energy occur within these atmospheres, they can break apart the hydrocarbons. This process releases carbon, which, in the intense pressure, can begin to crystallize into diamond structures. As these diamonds form, they can start to fall like rain. Imagine a rain of sparkling gems cascading down from the upper atmosphere of these distant worlds. However, it's important to note that the rain doesn't occur in the same manner as liquid rain on Earth. Rather, the diamonds would likely float and eventually settle on the dense, compacted layer deep within the atmosphere due to gravity. The unique combination of abundant carbon, extreme atmospheric pressure, and energy sources like lightning creates the perfect cocktail for diamond precipitation. So, while this celestial event may seem improbable, the conditions exist in the vastness of our universe, where nature exhibits its astonishing creativity. Astronomers initially became intrigued by the idea of diamond rain on certain planets through a combination of advanced technology and theoretical chemistry. It all began with the study of planets like Neptune and Uranus, which are classified as ice giants. These planets possess extreme atmospheric conditions characterized by high pressures and low temperatures. Using powerful telescopes and sophisticated modeling techniques, scientists analyzed the light spectrums emitted by these distant worlds. They observed that these planets have unique atmospheric compositions, including significant amounts of methane. When subjected to the intense pressures found in the deep interiors of these planets, scientists theorized that the methane could break down. In this high-pressure environment, carbon, an essential building block of diamonds, can crystallize into diamond structures. Essentially, the sheer pressure could force carbon atoms into arrangements that form diamonds. Researchers created simulations in laboratories that replicated the conditions found on these planets, where they observed that carbon could indeed transform into diamond under such extreme conditions. This combination of observational data from telescopes and experimental results led astronomers to entertain the possibility of diamond precipitation occurring within these far-off atmospheres. As a result, a fascinating hypothesis began to take shape: the notion that diamond rain might be a real phenomenon, occurring deep within the icy giants of our solar system. The concept of diamond rain, particularly linked to planets such as Neptune and Uranus, paints a fascinating picture of an alien world where carbon, under immense pressure and extreme temperatures, might crystallize into diamonds. This phenomenon has significant implications for a planet's geological structure. In a planet with conditions suitable for diamond formation, the process begins deep within the atmosphere. Here, the intense pressure can force carbon atoms together to forge diamond crystals. As these diamonds form, they can precipitate down through the atmosphere, much like rain, and settle into the planet's mantle. This introduces unique geological dynamics. The accumulation of such materials could create layers of diamonds, effectively altering the planet's mass distribution and thermal properties. The integrity of the planet's mantle could be impacted as well, as diamonds have distinct physical characteristics that differ from typical silicate minerals. Their presence could affect heat conduction and the behavior of mantle convection, which is crucial for the planet's overall thermal evolution. Over time, as diamonds form and accumulate, they could lead to specific geological features, possibly influencing tectonic activity and even the development of unique seismic behavior. Moreover, this diamond rain could result in a planetary environment where the electrical properties of the mantle are altered, potentially affecting magnetic fields and interactions with surrounding space. Such a dynamic system offers a glimpse into how varied and complex planetary geology can be beyond what we observe on Earth, highlighting the diversity of conditions and processes shaping planets in our universe. The existence of diamond rain not only challenges our understanding of planetary formation, but also enhances our appreciation for the myriad ways nature can manipulate elements and materials, creating structures we may have once deemed impossible. The phenomenon of diamond precipitation in a planetary atmosphere has significant implications for any potential life forms that might exist there. To understand this, envision a scenario where the atmosphere is rich in carbon and subjected to extreme pressure and temperature conditions. Under such circumstances, carbon can crystallize into diamonds, creating a dazzling, albeit harsh, environment. If life were to develop in such an atmosphere, it would face unique challenges. The presence of solid diamonds raining down could create a hostile surface environment. These crystalline structures, though beautiful, are incredibly hard and would likely fill the atmosphere with abrasive particles. Any organisms would have to adapt to this relentless barrage, possibly developing tough exteriors or protective layers to withstand the impacts. Moreover, the atmosphere's conditions may not support the fluid structures typically associated with life as we know it. Instead of water, which is essential for life on Earth, potential atmospheric life might rely on other solvents or structures to operate. The high density created by diamond precipitation could lead to a thick and heavy atmosphere, potentially affecting how organisms breathe or absorb nutrients. In this diamond-dense environment, the light might interact differently as well. The gemstones could scatter and refract sunlight in unexpected ways, possibly altering the photosynthetic processes of any plant-like life forms. Without the right adaptations, existing in a world with falling diamonds could make survival exceptionally precarious. Overall, while life in such a setting may display extraordinary adaptations to cope with the unique challenges posed by diamond precipitation, it would certainly look and function quite differently from life on our Earth. The idea of thriving amidst falling diamonds sparks the imagination, but it also highlights the complex interplay between environment and the concept of life itself. Imagine a world where rain doesn't fall as liquid, but as glittering gems. This is a reality on planets like Neptune and Uranus, where conditions are unlike anything we experience on Earth. The phenomenon of diamond rain vividly illustrates the extremes of temperature and pressure that exist in these distant realms. In the depths of these icy giants, the atmosphere is composed of a blend of hydrogen, helium, and methane. The methane plays a crucial role in this intriguing process. Under the intense pressure found in the interiors of these planets, far beyond what we could imagine, methane undergoes a transformation. When subjected to such tremendous gravitational forces, the molecules of methane break down and the carbon atoms within are freed. As these carbon atoms are compressed, they can bond together in a crystalline structure, forming diamonds. Simultaneously, the temperatures in these regions reach staggering heights. The combination of high pressure and elevated temperatures creates a unique environment that allows these diamonds to form and eventually precipitate down toward the core, much like raindrops falling through the atmosphere. This process is rather akin to how diamonds are created deep within Earth over millions of years, but on a cosmic scale, it happens rapidly beneath the surface of these planets. The presence of diamond rain doesn't just showcase a remarkable geological process, it also provides scientists with insights into the extreme conditions that govern planetary atmospheres far beyond our own. By studying these distant planets and their bizarre weather systems, researchers can better understand not only their composition and structure, but also the fundamental processes that occur throughout the universe, where extremes lead to extraordinary phenomena. Studying diamond rain provides fascinating insights into the processes occurring on other planets and can shed light on the history of our own. In the depths of gas giants like Saturn and Jupiter, extreme pressures and temperatures can cause carbon to crystallize into diamonds, forming rain that falls deep into the planet's interior. This phenomenon hints at unique chemical and physical environments vastly different from those on Earth. Understanding diamond rain helps scientists learn about the atmospheres of these planets. By researching how pressure, temperature, and composition lead to the formation of diamonds, we gain a clearer picture of their internal structures and behaviors. This knowledge can help us unravel the mystery behind gas giants' weather patterns, such as storms and winds, which behave in ways that are often unlike anything found on Earth. Furthermore, by studying diamond rain, researchers can draw parallels to carbon cycling on our own planet. The intriguing transformation of carbon into solid diamond under extreme conditions opens the door to understanding how carbon and other elements undergo various phases. This informs models of Earth's geology and atmosphere, illustrating how processes that seem alien could also reflect cycles that shape our planet over millions of years. Moreover, examining the conditions leading to diamond rain on other planets informs us about the possibilities of life elsewhere in the solar system. It raises questions about the diversity of environments that could harbor life, shapes planetary formation theories, and helps refine our search for habitable worlds beyond our own. The study of diamond rain stands at the intersection of planetary science and the quest to comprehend our place in the universe, revealing how interconnected we all are through the very elements that form us. The study of diamond rain stands at the intersection of planetary science and the quest to comprehend our place in the universe, revealing how interconnected we all are through the very elements that form us. Future missions aiming to collect or study diamonds found in space, particularly those possibly originating from distant stars or even from within our own solar system, would encounter a multitude of challenges. Firstly, navigating to the distant locations where these diamonds might exist presents a significant obstacle. Space is vast, and the journey could take many years, requiring advanced propulsion technologies and life support systems to sustain astronauts during prolonged periods in space. Once at the destination, the environment poses another set of difficulties. Many diamonds in space are created under extreme pressures and temperatures, particularly in the dense interiors of giant gas planets, where conditions are far harsher than anything we encounter on Earth. Extracting samples without causing contamination or damage would necessitate highly sophisticated equipment and techniques. This must ensure that the samples retain their unique properties and structures, which could hold invaluable information about their origin and the processes that formed them. Furthermore, diamonds in space might not resemble the sparkling gemstones we are familiar with. Depending on their formation processes, they could be trapped within ice, mixed with gases, or embedded in varied rocky materials. This variability means that scientists must prepare to develop specialized methods for identifying and isolating these specimens. Finally, analyzing these diamonds back on Earth poses yet another challenge. Some properties might only be observable under specific conditions that cannot be replicated outside their native environments. Bringing back samples for study necessitates ensuring they remain preserved throughout their journey back, which might involve creating containers that shield them from exposure to the conditions of Earth. All these factors mean that missions to study space diamonds will require innovative technology, extensive planning, and a selective approach to ensure that we can overcome these challenges and unlock the mysteries that these celestial treasures may hold. The discovery of diamond rain on certain planets has fundamentally altered our perspective on the diverse and extreme processes occurring throughout the universe. Initially, we often imagined planets as resembling Earth with similar atmospheres and geological characteristics. However, the realization that conditions on other worlds can create processes so alien to our experiences opens up new avenues of thought about planetary formation and evolution. On planets like Neptune and Uranus, immense pressures paired with high temperatures are believed to cause carbon to condense into solid forms, forming crystalline structures akin to diamonds. This phenomenon challenges our understanding of material behavior under extreme conditions, suggesting that substances we take for granted can morph into entirely different states based on their environmental circumstances. It highlights the adaptability of matter, reinforcing the idea that the universe operates under rules that can produce vastly different outcomes. Furthermore, this discovery sparks curiosity about the potential for similar processes elsewhere, prompting scientists to revise models of planetary atmospheres and interiors. It raises questions about what kinds of materials could exist on planets or moons with conditions vastly different from Earth's. Understanding diamond rain also feeds into broader conversations about the chemistry of life and the prerequisites for habitability in diverse environments. Overall, the existence of diamond rain signifies the creativity of nature in shaping worlds that are beyond our immediate experience. It encourages us to think critically about the vast possibilities that the universe holds, pointing to the complex and often surprising outcomes of cosmic processes. Each new example, like diamond rain, enriches our understanding and fuels our desire to explore the cosmos, searching for new worlds and the mysteries they might unveil. The planet infamous for its relentless firestorms is Venus, often described as Earth's twin because of its similar size and composition. However, its surface is a world of extremes, dominated by an atmosphere thick with carbon dioxide, which creates a greenhouse effect so intense that it raises temperatures to scorching levels. These firestorms are primarily caused by a combination of Venus's high temperatures, which can reach around the temperature of a hot oven, and its atmospheric pressure, which is about 90 times that of Earth at sea level. The constant heat creates an environment where sulfuric acid clouds form, and while these clouds seem benign, they contribute to a cycle that intensifies the heat further. When the surface heats up, it doesn't cool down efficiently due to the dense atmosphere. Instead, this baked environment leads to massive pressure systems that can generate powerful winds and storms. The combination of the extreme pressure, heat, and unique atmospheric chemistry fuels these firestorms, resulting in a chaotic, spinning tempest of volcanic activity and electrical storms driven by high winds that can whip around the planet at astonishing speeds. Venus stands as a stark reminder of how atmospheric conditions can lead to unimaginable extremes, turning what might look like a beautiful planet from a distance into a hellish landscape where fire and fury reign supreme. Firestorms have a significant impact on a planet's atmospheric composition and climate. As these intense blazes rage, they release enormous amounts of gases and particulate matter into the atmosphere. Smoke and soot, products of burning vegetation and organic materials, rise high into the air where they can travel vast distances. This not only adds carbon dioxide, a greenhouse gas, but also alters the balance of various atmospheric elements that play crucial roles in climate. The particles released can reflect or absorb sunlight, creating a shielding effect. This often leads to cooling in the areas directly beneath or downwind of the firestorm, while simultaneously warming the upper atmosphere where the particles reside. This dual effect can disrupt typical weather patterns, potentially causing drought in some regions while inducing unexpected downpours in others. Furthermore, firestorms produce a slew of reactive gases, including carbon monoxide, which can be harmful at ground level. These emissions interact with other atmospheric components, leading to the formation of smog and even altering the chemistry involved in cloud formation. With clouds influenced by these particles, the planet can experience variations in rainfall patterns, affecting ecosystems and water availability. The repercussions of firestorms extend beyond the immediate area of destruction. They contribute to shifting atmospheric dynamics and climate patterns, influencing everything from temperature fluctuations to precipitation changes, which can have long-lasting effects on the environment. Planets with magnetic fields serve as protective shields, influencing various atmospheric phenomena, including firestorms. Magnetic fields arise from the motion of molten iron in a planet's outer core. These invisible forces play a crucial role in how the planet interacts with solar wind, the constant stream of charged particles emitted by the sun. When solar winds reach a planet, they can strip away atmospheric particles. However, a strong magnetic field deflects these charged particles, reducing atmospheric loss over time. This is particularly relevant for planets like Earth, where the magnetic field protects it against harsh solar radiation. Moreover, magnetic fields can influence the behavior of charged particles within a planet's atmosphere, contributing to the formation of auroras. These phenomena can change the temperature and energy dynamics in the atmosphere, indirectly affecting weather patterns. In terms of firestorms, which often occur in conditions of high heat and energy, the stability and integrity of a planet's atmosphere are essential. A magnetic field that defends a planet from solar wind helps maintain that atmosphere, allowing for the right conditions to develop firestorms. Without this protective barrier, a planet could lose significant portions of its atmosphere over time, resulting in less heat-trapping gases and an inability to sustain the intense conditions needed for such explosive fire events. Thus, the magnetic field not only safeguards the atmosphere, but also plays a critical role in maintaining an environment where firestorms can thrive. The firestorms of certain planets, especially those in the gas giant category, can remind us of the intense weather phenomena we experience here on Earth. Just as Earth experiences thunderstorms fueled by warm, moist air, planets like Jupiter showcase massive storms, even larger than our planet, that create swirling winds and violent atmospheric activity. In fact, Jupiter's Great Red Spot is an example of a storm that has raged for centuries, driven by complex interactions within the planet's thick atmosphere. Moreover, the fierce electrical activity seen in these planetary storms is somewhat akin to the lightning strikes that electrify our thunderstorms. The mechanisms may vary significantly. Jupiter is composed mostly of hydrogen and helium, while Earth's atmosphere has a different mix. But the fundamental process of heat rising and creating turbulent wind patterns holds true across both realms. Interestingly, other bodies in our solar system exhibit firestorm-like phenomena as well. For instance, Saturn also sustains massive storms, some that spring to life suddenly and last for months, showcasing extraordinary bursts of energy. Mars features its own version of dust storms that can engulf the planet, creating swirling clouds that obscure the surface. Thus, while the environments may be profoundly different, certain dynamics of storm formation and energy interaction do share similarities across planets, linking these celestial bodies to our own tumultuous skies. The evolution of a planet's volatile environment is often the result of a complex interplay of historical processes that unfold over millions of years. To begin with, the formation of a planet like Earth involves the aggregation of dust and gas in space. As these materials coalesce, they generate intense heat. This primordial heating sets the stage for geological activity, including volcanic eruptions and the release of gases. As the planet cools, crust formation occurs, but it's not a smooth surface. The crust is divided into tectonic plates that float on the hotter, more fluid mantle beneath them. Over geologic time, these plates shift and collide, leading to earthquakes and the creation of mountain ranges. This constant movement contributes to a dynamic landscape that's continually reshaped by geological forces. Another critical factor in a planet's volatility is its atmosphere. Initially, young planets often have thick, toxic atmospheres, rich in carbon dioxide and sulfur. Volcanic activity contributes to this mix, releasing more gases that interact with the environment. Over time, atmospheric conditions can change significantly, which influences weather patterns and climate, fostering further geological instability. Additionally, external events play a crucial role. Asteroid impacts, for instance, can lead to dramatic climate shifts, changing the balance of gases in the atmosphere and creating long-term environmental consequences. These impacts can also cause widespread volcanic activity, injecting even more heat and pressure into the planet's crust. Finally, the movement of water is pivotal. If a planet has vast bodies of water, they can interact with the crust to create phenomena like erosion and sediment deposition, also affecting the stability of the environment. Water can dissolve minerals and transport them, contributing to the planet's chemical cycles, which also adds another layer to the volatility. The volatile environment of a planet results from a lineage of formative processes. The initial heat from formation, dynamic tectonic activity, atmospheric changes, external impacts, and the transformative presence of water. Together, these elements create an ever-changing landscape, alive with geological activity. Picture a vast, desolate landscape, transformed into an almost otherworldly scene during a firestorm on a distant planet. The sky is darkened by swirling clouds of ash and smoke, casting an eerie shadow over the terrain below. The air is thick and charged, filled with the acrid scent of burning materials as flames leap and dance across the ground. The surface itself might feature cracked, desiccated soil, blistered by extreme temperatures where patches of glowing lava can be seen breaking through. Jagged rock formations rise like sentinels against the chaos, their surfaces glowing red-hot from the heat. An expansive horizon could reveal rivers of molten lava flowing like liquid fire, illuminating the surroundings with an otherworldly glow. In this volatile environment, the winds howl, whipping up embers and debris, while occasionally fierce bursts of flame erupt, sending showers of sparks into the air. The landscape would be alive with sound, the roar of flames, the crackle of burning materials, and the soft rumble of shifting ground under the impact of the intense heat. Amid this chaos, survival would seem nearly impossible, as conditions become hostile in an instant. Yet, such firestorms also shape the planet's surface, creating unique geological formations over time as the fires consume, reshape, and ultimately allow new life to emerge from the ashes. Yet, such firestorms also shape the planet's surface, creating unique geological formations over time as the fires consume, reshape, and ultimately allow new life to emerge from the ashes. This harsh beauty, born from destruction, paints a vivid portrait of resilience in the cosmos. Scientists approach the study of intense and continuous storm systems by combining advanced technology with intricate modeling techniques. First, they utilize satellites positioned high above the Earth to capture vast swathes of data. These satellites observe storms in different wavelengths of light, allowing scientists to see beyond what the naked eye can perceive. They track cloud formations, lightning, and precipitation patterns, which helps identify storm development and behavior over time. In addition to satellite imagery, meteorologists rely on ground-based weather stations to gather localized data. These stations measure temperature, humidity, wind speed, and other atmospheric conditions at various altitudes. This information is vital as it provides a real-time look at what's happening on the ground, contributing to a comprehensive understanding of storms. Once data is collected, scientists employ computer models to simulate storm systems. These models are intricate simulations of the atmosphere based on the fundamental laws of physics. By inputting the gathered data into these models, researchers can predict how storms will evolve. The models can simulate interactions between different atmospheric layers and the effects of geography, helping scientists understand the factors driving storm intensity and frequency. As technology advances, new tools such as supercomputers allow for increasingly complex simulations that incorporate larger datasets and higher resolution. This means models can predict storms with greater accuracy. Scientists also explore machine learning techniques, enabling computers to recognize patterns within historical storm data. By learning from past storms, these systems can enhance predictive capabilities, targeting potential areas for severe weather more effectively. Ultimately, by combining satellite observations, ground data, advanced modeling, and innovative computing techniques, scientists aim to improve their understanding of intense storm systems. This holistic approach not only aids in predicting storms, but also enhances preparedness for how they may impact communities, agriculture, and ecosystems. When considering missions to observe or land on different planets, a plethora of potential hazards come into play. Each planet presents unique challenges that could impact the safety and success of such missions. For instance, extreme temperatures can pose significant risks. Some planets experience scorching heat during the day, while others plunge into chilling cold at night, creating conditions that can damage sensitive equipment or render systems inoperable. Atmospheric conditions also play a crucial role. Thick clouds may obscure visibility, making it difficult to maneuver spacecraft or conduct surface operations. Strong winds can disrupt landing procedures, while the presence of corrosive gases can damage equipment over time, presenting another layer of complexity to any mission. Surface conditions present their own dangers. Uneven terrain filled with deep craters, towering mountains, and vast plains of dust can complicate landings and rover navigation. Landing safely on an unstable surface can result in tipping over or becoming stuck, making it hard to explore further. Radiation exposure is another serious concern. Space missions must contend with high levels of cosmic radiation far beyond what we experience on Earth. This radiation can harm both human astronauts and electronic instruments, necessitating robust shielding or other protective measures for any crewed missions. Moreover, the uncertainties surrounding a planet's environment demand thorough pre-mission planning. Unpredictable dust storms could sweep across the surface, reducing visibility and possibly hindering communication with Earth. All these factors must be closely considered and accounted for to ensure mission success, ensuring that robust strategies are developed to mitigate these hazards before any launch. Firestorms, particularly those that occur on planets like Mars, can have significant implications for both the potential for life and the availability of resources. When we think of firestorms in a planetary context, we usually consider raging dust storms or intense wildfires, both of which can drastically alter the environment. Firstly, the presence of firestorms indicates an environment that can experience extreme conditions. For example, a firestorm might suggest fluctuations in temperature similar to those experienced during a typical Earth wildfire. Such drastic changes can create challenges for life as we know it, as many organisms require stable temperatures and consistent atmospheric conditions to survive. In extreme situations, firestorms can completely strip an area of its biological resources, eliminating habitats and the organisms that depend on them. On a more positive note, firestorms can also lead to the regeneration of resources. In many ecosystems, fire plays a role in rejuvenating the land, encouraging new growth by clearing out old and dead vegetation. This cycle of destruction and renewal can create opportunities for life to re-establish itself, potentially fostering a diverse range of plants and animals that can thrive in a temporarily changed landscape. From the perspective of known resources, firestorms can reshape the surface and chemical composition of a planet. For instance, on Mars, intense storms could expose subsurface ice or minerals that can be valuable for future exploration and even colonization. If water ice is unearthed, this could provide essential resources for future missions, fueling human exploration and potentially supporting life. Overall, while firestorms may pose immediate threats to the survival of life and can deplete vital resources, they can also pave the way for new growth and create opportunities for scientific discovery. Understanding these complex interactions allows us to appreciate the resilience of ecosystems as well as the potential for resources that may lie hidden beneath the surface, waiting to be uncovered. One of the most astonishing findings about planetary firestorm patterns, particularly on Jupiter, is how these storms can persist for years or even centuries. Imagine a hurricane on Earth, which typically runs its course in a matter of days or weeks. Now, consider that on Jupiter, storms like the Great Red Spot have been raging for over 300 years, showcasing a level of stability and persistence that baffles scientists. Moreover, the behavior of these enormous storms can be quite unpredictable. As they interact with each other, they can merge, spin off new storms, or even suddenly change direction. This dynamic, akin to a chaotic dance of atmospheric currents, reveals a complexity in weather patterns that goes beyond what scientists originally anticipated. Another surprising aspect is the scale of these firestorms. They can be so vast that a storm could easily swallow entire planets whole. The sheer energy involved is mind-boggling, with winds that can exceed the speed of sound in some cases. This intensity not only challenges our understanding of physics, but also drives home the notion that different celestial environments can produce weather phenomena far beyond our terrestrial experiences. Ultimately, these patterns reveal sections of the universe that remain lively and ever-changing, begging the question of what other secrets planetary weather might hold. As we deepen our exploration, we uncover more mysteries tied to these majestic firestorms that continue to captivate our imaginations and challenge our scientific understanding. The icy planet known for its violent methane hailstorms is Neptune. Unlike any other planet in our solar system, Neptune's atmosphere is truly fascinating due to its dynamic weather patterns and extreme conditions. At first glance, Neptune may seem serene with its deep blue hue, but beneath that calm exterior lies a potent atmosphere composed primarily of hydrogen, helium, and a significant amount of methane. The presence of methane is what gives Neptune its striking color, absorbing red light and reflecting blue. However, this beautiful exterior masks the planet's tumultuous nature. In Neptune's upper atmosphere, fierce winds whip around at astonishing speeds, sometimes reaching more than 1,000 miles per hour. These intense winds create storms that are not just any thunderstorms. They are driven by a supply of energy that seems to come from within the planet rather than from the sun. This internal heat fosters a unique climate where methane can condense and freeze, resulting in hail-like formations that can crash down during these brutal storms. These methane hailstorms can be incredibly violent, with the hail reaching the surface and delivering a shockingly cold impact. This atmospheric behavior, combined with the planet's vibrant colors and extreme weather, emphasizes Neptune's position as one of the most intriguing bodies in our solar system, showcasing a blend of beauty and chaos in a distant, icy realm. Hailstorms are fascinating phenomena that occur under specific atmospheric conditions. They typically form in strong thunderstorms where warm, moist air rises rapidly in a process called convection. As this warm air moves upward, it encounters cooler air at higher altitudes. This collision causes the water vapor in the warm air to condense into tiny water droplets, which then freeze as they ascend through the colder layers of the atmosphere. The crucial factor triggering the intensity of a hailstorm is the strength of these updrafts. When the updrafts are exceptionally strong, they can lift water droplets high enough where they freeze into ice pellets. These pellets get caught in the turbulence of the storm, being continuously lifted and then falling a short distance before being pushed up again. This back-and-forth motion allows the pellets to grow larger as additional layers of water freeze onto them. When the hailstones finally become too heavy for the updrafts to support, they fall to the ground. The size of hailstones can vary significantly depending on how powerful the updrafts are and how much moisture is available in the storm. Intense thunderstorms, especially those associated with severe weather conditions, produce the largest hail. Moreover, environmental factors like the temperature and humidity levels can also influence the storm's strength, contributing to the severity of the hail it produces. Thus, a combination of strong updrafts, abundant moisture, and favorable atmospheric conditions creates the ideal setting for hailstorms to develop, sometimes resulting in hailstones that can cause extensive damage. Methane hailstorms are truly fascinating phenomena that occur in extreme environments, particularly on planets like Saturn's moon Titan. On Titan, the atmosphere is thick enough to support weather patterns that bear resemblance to those on Earth, but with a unique twist. Imagine storms developing within an atmosphere where it rains not water, but methane, an abundant hydrocarbon that exists as a gas at room temperature. The scale of these storms is significant. They can cover vast swaths of Titan's surface, similar to how rainstorms might sweep across a region on Earth. These methane hailstorms are composed of drops of liquid methane that can grow large enough to fall to the ground like hailstones, causing a dramatic reshaping of the landscape. When they strike the surface, the energy released can erode terrain, create new features, and even carve out river-like channels in the frigid surface ice. This process of erosion is intricately linked to Titan's complex geology and can lead to the development of vast, organic-rich wetlands. The impact on the planet's surface can be profound. Just as heavy rainfall on Earth can lead to flooding and alter landscapes, methane hailstorms on Titan can result in catastrophic changes that challenge our understanding of surface processes beyond our own planet. Over time, these storms contribute to a cycle of methane clouds forming, raining down and reshaping the icy crust, creating a dynamic environment that persists over long timescales. This sets the stage for an atmospheric and geological interplay that keeps Titan an exciting subject of study in planetary science. Methane plays a significant role in shaping a planet's climate and weather systems, primarily because this gas is much more effective at trapping heat in the atmosphere than carbon dioxide. This makes methane a potent greenhouse gas. To understand its impact, imagine the atmosphere acting like a thick blanket surrounding the Earth, keeping warmth close to the surface. When methane is present, this blanket becomes even warmer. Increased methane levels can lead to rising global temperatures, disrupting established weather patterns. As the atmosphere heats, it can intensify storms, leading to more extreme weather events like hurricanes, heavy rainfall, and droughts. Think of weather systems as interconnected engines. When one engine heats up, others may speed up or malfunction, causing chaotic and unpredictable weather. Additionally, the presence of methane can influence the hydrological cycle, which governs how water moves through the atmosphere. Warmer conditions can lead to increased evaporation, contributing to heavier rainfall in some regions, while causing dry spells in others. This duality can have profound implications for ecosystems, agriculture, and water resources. The changes affect everything from the growth patterns of crops to the health of natural habitats. Moreover, as temperatures rise, natural reservoirs of methane, such as wetlands and permafrost, can release even more of this gas into the atmosphere. This creates a feedback loop. As more methane is released, temperatures rise further, leading to even more methane emissions. Understanding this dynamic is crucial for addressing climate change, as managing methane levels could be key to stabilizing the climate and mitigating extreme weather patterns. As scientists study these interactions, the importance of monitoring and reducing methane emissions grows ever clearer. Hailstorms beyond Earth, particularly on planets like Jupiter, share some similarities with those we experience on our home planet, yet they also exhibit remarkable differences due to the distinct atmospheric conditions that exist in those environments. Both types of storms are born from powerful updrafts within storm systems. On Earth, these updrafts lift water droplets high into colder regions of the atmosphere, where they freeze into ice pellets that eventually fall as hail. Similarly, on Jupiter, the violent storms are so intense that they can create powerful updrafts, allowing water and ammonia to freeze and form hail-like structures. However, the composition of these particles is quite different, as they might include elements other than just water, like ammonia and methane, which are prevalent in Jupiter's atmosphere. The size of hailstones plays a significant role in distinguishing earthly hailstorms from their extraterrestrial counterparts. On Earth, hailstones can reach sizes comparable to golf balls, but those formed on Jupiter can potentially grow to be much larger. Imagine the size of a baseball, or even larger, due to the incredibly strong forces at play in the planet's atmosphere. The active weather systems on Jupiter, influenced by its rapid rotation and dense atmosphere, can maintain hailstones aloft longer, allowing them to gather more mass before they eventually fall. Another difference lies in the frequency and scale of these storms. Earth experiences localized hailstorms, often limited to specific geographic areas. In contrast, Jupiter's storms can span vast regions of the planet and are part of a grander scale of atmospheric turbulence, creating a series of storms that can be more widespread and persistent. Moreover, the atmospheric conditions between the two worlds differ vastly. The clouds on Earth are primarily comprised of water vapor, whereas Jupiter's clouds feature a complex mix of gases, including ammonia and water, dramatically affecting the formation and characteristics of hail-like precipitation. While hailstorms on Earth and other planets like Jupiter share foundational processes in their formation, they diverge significantly in terms of composition, size, frequency, and the underlying atmospheric conditions that create these phenomena. Understanding these similarities and differences offers fascinating insights into the dynamics of weather across our universe. Scientists employ a fascinating array of technologies to investigate extreme weather phenomena on distant planets, leveraging both remote sensing and sophisticated modeling techniques. One of the primary tools in this exploration is the space-based observatory, which captures images and data across various wavelengths, such as infrared and radio. These observatories allow scientists to visualize atmospheric patterns, temperature variations, and even storm systems from afar. Telescopes equipped with specialized instruments can analyze the composition of a planet's atmosphere, identifying gases and particles. By examining the light that passes through an atmosphere or is reflected off a planet's surface, researchers can deduce key information about weather conditions and environmental stability. In addition to telescopes, spacecraft equipped with weather monitoring instruments actively measure atmospheric pressure, temperature, and wind speeds. These probes, sent to study planets like Mars and the gas giants, gather first-hand data that can reveal insights into phenomena such as dust storms or the formation of hurricanes. Computer simulations are another crucial technology where scientists create models of planetary atmospheres. By inputting data collected from observations, these simulations can forecast weather patterns and explain the underlying physical processes that drive them. This combinative approach of remote observation, direct measurement, and advanced modeling allows scientists to piece together a dynamic picture of how extreme weather behaves on these distant worlds. Through these technologies, we can gain a deeper understanding of the forces shaping planets vastly different from our own. Methane hailstorms illuminate our understanding of atmospheric chemistry by showcasing how different environmental conditions can lead to the formation of unique weather phenomena. On planets like Saturn's moon Titan, where the atmosphere is thick and rich in methane, this compound can exist in various states: gas, liquid, and solid. In this alien environment, temperatures plummet low enough for methane to rain down, forming pools and lakes. When conditions shift, coupled with seasonal changes or shifts in atmospheric pressure, this liquid methane can freeze and then fall as hail. The formation of methane hail not only points to the presence of complex hydrocarbon cycles, but it also provides insight into how energy moves through the atmosphere. As we study these hailstorms, we learn about the chemical reactions that occur when methane interacts with other molecules present in Titan's atmosphere. These interactions can lead to the creation of more complex organic compounds, which are fundamental to understanding not only the chemistry of Titan, but also prebiotic conditions elsewhere in the universe. Such storms also serve as analogues for potential weather patterns on Earth, highlighting how different planetary bodies can exhibit diverse forms of atmospheric behavior due to their distinct compositions and conditions. The study of methane hailstorms deepens our appreciation of chemical diversity in the universe and fuels our search for environments that may harbor life. By analyzing these processes, scientists can create models that predict how atmospheres evolve and interact with their surfaces, ultimately enhancing our grasp of planetary science. When we imagine methane hail, we enter a fascinating realm of theoretical geology and atmospheric science. As methane exists as a gas on Earth but can condense into slushy or icy forms in colder regions, the idea of hail made from methane presents intriguing possibilities. One significant effect of these methane hail impacts on geological structures would be the formation of unique crater-like depressions on planetary surfaces. Over time, repeated impacts from these hailstones could lead to the eroding of rocks and the layering of organic materials. The cold nature of methane means that when it interacts with other substances like rock or even other ice, it could lead to a range of physical and chemical reactions. These interactions could alter the material properties of the impacted surfaces. For example, layering could occur if methane left behind ice or other residues that gradually build up over time, potentially creating new geological features distinct from typical erosion patterns we see on Earth. As we consider the long-term implications, one might envision that a consistent pattern of these impacts would alter local ecosystems and hydrological systems. The substances released during these impacts could contribute to the formation of unusual geological formations or even new habitats supporting different forms of life. If the methane transformed into liquid in warm, post-impact environments, it could act as a solvent, breaking down minerals in a manner similar yet distinct from water. Overall, while the concept of methane hail is hypothetical, its imagined effects on geological structures over time could lead to a fascinating interplay of erosion, deposition, and chemical reactions, yielding a unique landscape shaped by this otherworldly phenomenon. Scientists continue to explore such ideas as they broaden our understanding of planetary processes beyond Earth, sparking curiosity about what forms life and landscapes might take elsewhere in our universe. The idea of harvesting methane hail opens a fascinating window into both the possibilities of scientific inquiry and practical applications. In some regions of our solar system, Particularly on moons like Titan, methane exists not just as a gas, but also in solid forms, including hail-like structures. Unlike the water ice we are familiar with on Earth, these frozen droplets are composed of methane, a hydrocarbon that plays a significant role in energy and atmospheric chemistry. If scientists were able to collect methane hail, it could serve various purposes. For one, it could deepen our understanding of planetary atmospheres and weather systems in extraterrestrial environments. Analyzing methane hail would allow researchers to study the conditions under which it forms, its interaction with other atmospheric components, and its role in the larger dynamic of the Moon's climate. Moreover, methane itself is a valuable resource. On Earth, it's recognized as a major energy source, often used for heating and electricity generation. If we could find ways to collect and utilize methane hail in an off-world scenario, future missions could rely on it as a fuel source. This would be particularly significant for long-duration space travel, where utilizing local resources can reduce the need to transport fuel from Earth. Additionally, methane can serve as a building block for complex organic molecules, which raises exciting possibilities for astrobiological research. If we discover life or the necessary ingredients for life beyond our planet, understanding how methane interacts with other compounds could be crucial in piecing together how such life might develop or exist. Harvesting methane hail, while currently more of a theoretical pursuit, underscores the incredible ingenuity required in space exploration and the importance of developing technologies to utilize extraterrestrial resources. As we look toward future missions, the potential utility of harvesting these unique forms could profoundly impact both science and the logistics of human endeavors beyond Earth. In the vast expanse of our universe, icy worlds such as Europa and Enceladus present intriguing possibilities for life. These moons, which orbit gas giants, are enveloped in thick layers of ice, under which scientists believe there may be vast oceans of liquid water. This opens the door to the concept of life thriving in extreme conditions, far removed from the familiar warmth and nurturing conditions of Earth. One speculative idea is that life in these icy environments might rely on chemosynthesis instead of photosynthesis. While photosynthesis uses sunlight to convert carbon dioxide and water into sugars, chemosynthesis taps into chemical reactions, sometimes involving the minerals found on the ocean floor. Microbes could potentially harness energy from the chemical reactions between water and minerals, much like those found near hydrothermal vents on Earth. Additionally, the harsh conditions of these icy surfaces might lead to the evolution of life forms that are fundamentally different from what we know. Imagine organisms that have adapted to withstand intense cold, extreme pressure, and potentially high levels of radiation, all while being insulated under layers of ice. Researchers speculate these life forms could possess unique biochemical processes, using antifreeze proteins to prevent their bodily fluids from freezing, or even leveraging unusual cellular structures designed to protect against harsh environmental factors. The concept of extremophiles, organisms that thrive in extreme environments, gives us a glimpse into the possibilities. On Earth, we already find life in boiling hot springs, the depths of ocean trenches, and even in highly acidic lakes. This resilience suggests that if life can develop on our planet in such extreme conditions, similar forms could exist elsewhere, adapting to the icy habitats of other celestial bodies. Overall, the potential for life to evolve in these submerged, frigid oceans sparks the imagination and underscores the incredible adaptability of life. These speculations fuel ongoing missions and research as scientists seek to uncover the secrets of our solar system and perhaps even discover entirely new forms of life in the cosmos. The planet known for its toxic clouds of sulfuric acid is Venus. Imagine a thick, oppressive atmosphere that envelops a planet, creating a veneer of mystery and danger. Venus's clouds are not just ordinary clouds. They are composed of tiny droplets of sulfuric acid mixed with other gases like carbon dioxide, making the atmosphere incredibly hostile. These clouds form through a complex set of chemical reactions that begin with the abundant sulfur dioxide present in the atmosphere. When sunlight strikes this sulfur dioxide, it initiates a series of reactions that result in the formation of sulfuric acid. This process is accelerated by the planet's extreme temperatures and pressures, which serve to create dense, hot conditions. The sulfuric acid droplets coalesce, leading to thick, swirling layers of clouds that can obscure the planet's surface. Moreover, Venus's atmosphere is often regarded as a runaway greenhouse effect. The dense carbon dioxide traps heat efficiently, leading to surface temperatures hot enough to melt lead and further facilitating the cloud formation process. As these toxic clouds spiral around the planet, they create a stunning yet perilous environment, highlighting Venus's status as one of the most inhospitable places in our solar system. Sulfuric acid plays a significant role in the atmospheric dynamics of certain planets, particularly in our solar system, like Venus. The planet known for its toxic clouds of sulfuric acid is Venus. Imagine a thick, oppressive atmosphere that envelops a planet, creating a veneer of mystery and danger. Venus's clouds are not just ordinary clouds. They are composed of tiny droplets of sulfuric acid mixed with other gases like carbon dioxide, making the atmosphere incredibly hostile. These clouds form through a complex set of chemical reactions that begin with the abundant sulfur dioxide present in the atmosphere. When sunlight strikes this sulfur dioxide, it initiates a series of reactions that result in the formation of sulfuric acid. This process is accelerated by the planet's extreme temperatures and pressures, which serve to create dense, hot conditions. The sulfuric acid droplets coalesce, leading to thick, swirling layers of clouds that can obscure the planet's surface. Moreover, Venus's atmosphere is often regarded as a runaway greenhouse effect. The dense carbon dioxide traps heat efficiently, leading to surface temperatures hot enough to melt lead and further facilitating the cloud formation process. As these toxic clouds spiral around the planet, they create a stunning yet perilous environment, highlighting Venus's status as one of the most inhospitable places in our solar system. Sulfuric acid plays a significant role in the atmospheric dynamics of certain planets, particularly in our solar system, like Venus. Imagine atmospheric clouds that are thick, heavy, and laden with droplets of sulfuric acid. These clouds reflect sunlight away from the planet, creating a greenhouse effect that traps heat within the atmosphere. This process leads to extraordinarily high surface temperatures, far hotter than what one might expect given the planet's distance from the Sun. The presence of sulfuric acid also influences weather patterns. As these clouds form and evolve, they can lead to heavy precipitation in the form of acid rain, although the extreme surface conditions make it different from what we experience on Earth. This acid rain can shape the landscape and contribute to a cycle of erosion and chemical reactions on the surface. Additionally, the thick sulfuric acid clouds create a unique atmospheric circulation, where towering storm systems can develop, giving rise to a variety of weather phenomena. The dense atmosphere, combined with the heat retention caused by sulfuric acid, results in a stable yet dynamic climate. Overall, sulfuric acid significantly alters temperature regulation and the character of weather patterns, leading to an environment that is both hostile and intriguing. The emergence of toxic clouds in a planet's atmosphere can have profound consequences for its ecology. These clouds, often composed of harmful gases and particulates, can lead to significant disruptions in ecosystems. To begin with, they can affect air quality, making breathing difficult for both animal and plant life. When creatures inhale these toxins, it can cause health issues, reduce reproductive success, and ultimately impact population dynamics. Plants are not immune to this threat. Toxic clouds can hinder photosynthesis, the vital process through which plants convert sunlight into energy. If plants cannot photosynthesize effectively, their growth and health decline, reducing food availability for herbivores. This ripple effect can alter entire food webs, from the smallest insects to the largest predators, disrupting the balance that keeps ecosystems stable. Moreover, precipitation can carry some of these toxic elements down to the ground, leading to soil and water contamination. This makes the environment hostile for many organisms, with potential long-term effects on plant diversity and soil health. With changes in soil quality, the types of plants that can thrive in that area may shift, further altering habitats and the species that depend on them. The introduction of toxins into aquatic ecosystems is equally troubling. Rainfall can wash harmful substances into rivers or lakes, affecting fish and other aquatic life. Contaminated water sources can lead to fish die-offs, shifts in species distribution, and bioaccumulation of toxins in food chains, which can pose health risks not just to wildlife, but also to humans who rely on those water resources. Toxic clouds can initiate a cascade of ecological consequences. The delicate balance of life within ecosystems is threatened, leading to potential loss of biodiversity, altered community dynamics, and long-lasting damage to the environment. Understanding these impacts is crucial as we assess the health of ecosystems and work towards solutions that mitigate such pollution. When exploring a planet with a harsh, corrosive atmosphere, instruments and spacecraft are meticulously designed to endure extreme conditions. Engineers use materials with high resistance to corrosion, such as certain metals and specialized coatings, to ensure that the surfaces can withstand reactive gases or particles found in the atmosphere. Additionally, thorough testing is performed to see how the spacecraft materials interact with environmental conditions, particularly focusing on factors like temperature variations and humidity levels that may exacerbate corrosion. This is akin to a test of endurance, where prototypes undergo accelerated aging to reveal their potential weaknesses before actual missions commence. To further enhance resilience, protective barriers may be incorporated into the design. Just as we wear jackets to shield ourselves from the weather, instruments might be encased in specially designed compartments that limit exposure to the external atmosphere. These compartments can include filters that trap corrosive particles before they reach sensitive electronics. Moreover, monitoring systems are built into spacecraft to detect corrosion-related issues in real time. These monitoring systems can provide critical data to mission control, enabling timely adjustments or repairs if necessary. This multifaceted approach ensures that every piece of technology aboard is prepared for the challenges posed by a planet's atmospheric conditions, paving the way for successful explorations into the unknown. The sulfuric acid clouds that envelop Venus create a challenging environment for visibility and exploration. These clouds form a thick blanket of haze that obscures the planet's surface from view. Imagine trying to see through a dense fog. That's essentially what scientists encounter when they attempt to observe Venus. The clouds reflect sunlight and scatter light in all directions, resulting in a predominantly yellowish glow that makes it hard to discern details on the ground. This lack of visibility makes traditional visual observations via telescopes nearly impossible. Instead, scientists rely on radar and infrared technology to pierce through these clouds, allowing them to map the surface and analyze geological features. For example, radar waves can penetrate the cloud cover and bounce back from the terrain below, revealing mountains, valleys, and other formations that are otherwise hidden. The thickness of these sulfuric acid clouds not only limits visibility, but also contributes to extreme atmospheric pressure and high temperatures on the surface. This oppressive environment poses significant challenges for lander missions designed to explore the planet directly. Any equipment sent to the surface must withstand corrosive conditions, where sulfuric acid can damage materials and endure crushing pressure that far exceeds that of Earth. As a result, while the clouds obscure Venus from plain sight, they also provide a canvas for innovative exploration methods, encouraging scientists to develop advanced technologies that can survive and operate under such harsh conditions. This interplay between cloud cover and exploration hints at the complexities that make Venus an object of fascination in the quest to understand more about our solar system. The presence of sulfuric acid in a planet's atmosphere can dramatically influence the mineral compositions found on its surface. To visualize this, consider a landscape that's constantly bombarded by acid rain. Over time, this rainfall would interact with the minerals present, leading to a variety of chemical reactions. Sulfuric acid, being a potent acid, has the ability to break down many silicate and carbonate minerals, effectively altering their structure and composition. As it seeps into the ground or reacts with surface rocks, new minerals can form while others may dissolve away. This process can lead to the creation of sulfate minerals, characterized by their unique chemical signatures. Additionally, the high acidity can prevent certain minerals from forming while promoting the growth of others that thrive in such conditions. For instance, while minerals like quartz might remain stable, the presence of sulfuric acid could facilitate the formation of distinctive sulfide and sulfate minerals, which may not be common on Earth. Over extensive periods, this acid-rich environment could lead to a wide range of geological phenomena, such as the development of unusual landforms and even the reworking of entire rock layers. The interplay between sulfuric acid, minerals, and environmental conditions creates a dynamic system where the surface composition is in constant flux, showcasing an ever-evolving geological landscape. The presence of sulfuric acid on a planet provides significant insights into its geological activity, particularly volcanic or tectonic processes. Sulfuric acid often forms as a result of volcanic eruptions, where sulfur dioxide, a common gas emitted from volcanic activity, interacts with water in the atmosphere. This chemical reaction creates sulfuric acid clouds, which can lead to acid rain on the planet's surface. When we observe sulfuric acid, it indicates that the planet has experienced some form of volcanic activity in its past or is still actively venting gases into the atmosphere. This suggests that there is ongoing geological processes at work that can recirculate sulfur and potentially reshape the landscape. High levels of sulfuric acid can also mean that the planet's surface may exhibit signs of erosion or alteration, reflecting changes driven by weather systems influenced by volcanic gases. Furthermore, if tectonic activity is present, it could be linked to the movement of crustal plates, which facilitates the release of sulfur compounds from the planet's interior. Sulfuric acid is a strong indicator of a planet's dynamic geological environment, revealing a history of volcanic eruptions and suggesting a continued interplay between the interior and atmosphere, contributing to a complex and evolving planetary ecosystem. Acidic environments, like those found on Venus, are extreme examples of hostile atmospheres. Imagine standing on a planet where clouds of sulfuric acid rain down, creating an atmosphere that is thick and incredibly hot. This contrasts sharply with several other toxic environments observed in our universe. For instance, the atmosphere of Jupiter is predominantly made up of hydrogen and helium, but it also contains ammonia and methane, substances that could be fatal to living organisms as we know them. The intense pressure and swirling storms add an extra layer of danger, making it not only toxic, but also inhospitable due to extreme conditions. Meanwhile, on planets like Titan, Saturn's largest moon, the environment is rich in methane and ethane. These compounds exist as liquid lakes, creating a peculiar landscape that would be alien to life as we know it. Despite the presence of organic materials, Titan's surface conditions are so frigid that traditional carbon-based life cannot thrive. When comparing these environments, the acidic clouds of Venus stand out due to their blend of extreme temperatures and corrosive chemical compounds. In many ways, they embody one of the most punishing atmospheres in our solar system, yet they are not alone in the category of toxicity. Each of these celestial bodies showcases different forms of hostility that challenge the very notion of habitable worlds, highlighting the extraordinary variety of conditions that exist across the universe. The concept of terraforming, or changing the environment of a planet to make it habitable, captivates the imagination and presents real scientific challenges and opportunities. For instance, envision Mars, a cold and arid landscape where scientists propose introducing certain gases to thicken its thin atmosphere and warm the surface. By releasing greenhouse gases like carbon dioxide, we could potentially trap more heat, and create conditions that might support liquid water. Another approach involves enhancing the planet's surface with living organisms, introducing specially engineered bacteria or algae that can thrive in harsh conditions might jumpstart a new ecological cycle. These organisms could convert carbon dioxide into oxygen through photosynthesis, slowly reshaping the atmosphere to include more breathable air. The synergy between biological processes and environmental conditions would be key to this transformation. On a broader scale, altering an atmosphere might also involve manipulating planetary weather systems. Theoretical concepts such as space mirrors to reflect sunlight and increase temperatures, or giant orbital satellites that could manage solar radiation, are intriguing possibilities. These technological advances could facilitate long-term climate control on the surface. However, each method carries significant ethical and environmental implications. The unpredictability of altering planetary systems means we must consider potential risks and unintended consequences carefully. Terraforming not only challenges our scientific abilities, but also prompts us to think deeply about our responsibilities as stewards of other worlds. While the possibilities are rooted in theoretical exploration, the drive to make distant planets more Earth-like embodies humanity's quest to expand our horizons and ensure our survival in the cosmos. The journey to discover whether we can change others' atmospheres is as exciting as the potential benefits of creating new homes beyond our own. The discovery of hostile environments on other planets profoundly reshapes our understanding of what makes a world suitable for life. Traditionally, we envisioned habitable planets as having Earth-like conditions, mild temperatures, liquid water, and a breathable atmosphere. However, as scientists explore exoplanets, planets located outside our solar system, many reveal extreme conditions that might seem wholly uninhabitable. Take, for instance, the gases and temperatures of planets in the so-called hot Jupiter category. These massive, gas-rich worlds orbit very close to their stars, producing scorching surfaces far too hot for life as we know it. Yet, researchers are increasingly considering alternative forms of life that could emerge in such environments. It challenges the long-held belief that life can only thrive in familiar Earth-like habitats. Moreover, the exploration of moons like Europa and Enceladus, which are characterized by frigid conditions beneath their icy surfaces, showcases yet another layer of complexity. Here, the potential presence of subsurface oceans warmed by geological activity suggests that life may exist in complete darkness, far away from the sun's energy. This realization pushes scientists to broaden the criteria for habitability beyond mere surface conditions. Additionally, examining the atmospheres of planets where extreme temperatures or pressures exist might unveil chemical processes that could hint at life even when conditions seem severe. Understanding these environments encourages a shift in perspective, embracing the idea that life could arise from unexpected chemical reactions or adapt to survive in harsh conditions. The discovery of hostile environments invites us to rethink the essential elements of habitability, persuading us to consider a diverse range of planetary conditions where life might emerge, adapting to thrive where we once thought it impossible. This evolving perspective not only expands our search for extraterrestrial life, but also deepens our appreciation for life's resilience and versatility in the universe. The planet that is famously tidally locked is Mercury, although its relationship with the Sun is more complex than that of a typical tidally locked body. Instead of a one-to-one lock, Mercury rotates 3 times on its axis for every 2 orbits around the Sun. This unusual rotation results in a unique dynamic between its day and night cycles. In a tidally locked scenario, one side of the planet constantly faces its star, while the opposite side remains in perpetual darkness. For Mercury, this creates stark environmental differences. The side facing the Sun endures extreme temperatures, soaring to unbearable highs during the long daytime, where solar rays bathe the surface continuously. Conversely, the night side experiences freezing cold, as it lacks sunlight for extended periods. As a result, These temperature extremes lead to a lack of an atmosphere capable of sustaining weather systems, producing a surface that is barren and desolate, covered in craters from countless impacts over billions of years. The rotation's effects also lead to a very slow transition between day and night, resulting in long periods for each half of the planet. This environment starkly contrasts planets with more balanced day-night cycles, where climates can support a variety of atmospheric and weather phenomena. The unique rotational characteristics of Mercury, while an exception among planets, showcase how a planet's relationship with its rotation and its star can shape its environment and surface conditions in profound ways. On planets that have a slow rotation or are tidally locked, one side experiences perpetual daylight, while the other remains engulfed in darkness. This stark contrast in illumination creates dramatic differences in climate and environmental conditions. The side that is perpetually sunlit becomes exceedingly warm. Without the relief of night, temperatures can soar to extreme heights, creating a desert-like environment. The continuous sunlight leads to significant evaporation of any existing water sources, contributing to a dry atmosphere. Plants and animals that might thrive in such conditions would need adaptations to withstand high temperatures and limited moisture, perhaps developing reflective surfaces or capabilities to conserve water. Conversely, the dark side of the planet enters a different kind of climate reality. With no exposure to sunlight, it experiences frigid temperatures. This constant chill can lead to the formation of ice and snow, creating a landscape that is stark and inhospitable. The lack of warmth also means that any remaining water can freeze, making the environment even harsher, with little chance for life as we know it to exist without significant adaptations. Transition zones between the light and dark sides, often referred to as the Terminator, experience interesting dynamics. Here, there can be a mixture of warm and cold climates, leading to unique weather patterns. Wind can shift dramatically in this region as air masses from the hot and cold sides meet, resulting in turbulent conditions. This blending area might host the most diverse ecosystems, attracting organisms adapted to fluctuating environmental extremes. Understanding these contrasting climates helps us appreciate how life might adapt in such alien worlds, highlighting the resilience and diversity of life forms that could potentially inhabit planets under very different conditions than those on Earth. Extreme temperature differentials on a planet can have profound effects on its surface and atmospheric conditions. Imagine a scenario where one side of the planet basks continuously in brilliant sunlight, while the other side remains cloaked in perpetual darkness. The intense heat on the sunlit side can lead to scorching surface temperatures, causing materials to undergo changes. Rock may crack, water may evaporate, and soils can dry out, creating a barren landscape. Conversely, the dark side would present a stark contrast. Here, the absence of sunlight leads to frigid temperatures, potentially allowing ice and other frozen compounds to dominate the environment. These extreme contrasts create significant challenges for any form of life that might exist, as the varied temperatures can drastically affect everything from microbial survival to vegetation growth. The interaction between these hot and cold regions also influences atmospheric behavior. As warm air rises from the heated side, it creates areas of lower pressure, leading to turbulent winds as cooler air rushes to fill the gap. This results in dynamic weather patterns, with storms forming as air masses collide. Such shifts can also lead to the development of thick atmospheric layers where clouds gather and precipitation occurs, potentially birthing intense storms. Over time, these processes can profoundly shape the planet's surface features. Erosion from powerful winds and dust storms can alter landscapes, while thermal expansion and contraction can lead to cracking and breakage of surface materials. The extreme temperature variations not only sculpt the physical state of the planet, but also dictate the rhythm of its atmospheric processes, creating a continuously shifting environment marked by the dance between heat and cold. Scientists are fascinated by the resilience of life, especially when considering how organisms might adapt to extreme conditions on other planets. Take For instance, environments that are characterized by high levels of radiation, extreme temperatures, and suffocating pressures. These conditions might seem inhospitable, yet certain forms of life on Earth, known as extremophiles, thrive under such duress. To understand adaptation, imagine a tiny organism that lives in a hot spring. This creature has developed specialized proteins that remain stable and functional even at scorching temperatures. Similarly, on other planets, hypothetical life forms might evolve unique structural adaptations, such as thicker outer membranes to protect against radiation or specialized biochemical pathways that allow them to metabolize substances that are deadly to most organisms. Moreover, survival might hinge on a life form's ability to enter a dormant state, enabling it to endure unbearable conditions until the environment becomes more suitable. For instance, certain microbes on Earth can remain viable for years, even in a desiccated state, waiting for moisture to return. In the harsh conditions of another planet, something analogous might occur. Through genetic mutations and natural selection over long periods, these hypothetical organisms could develop features that enhance their survival, such as the capacity to utilize available resources in peculiar ways, or developing symbiotic relationships with other life forms to maximize their chances of survival. Thus, while the environments of other planets might be extreme, the possibilities for how life could adapt are vast and varied, showcasing the incredible ingenuity of nature. The geological features of a tidally locked planet are profoundly influenced by the gravitational interaction between the planet and its star. In this scenario, one side of the planet continually faces the star, while the other side remains in perpetual darkness. This creates stark contrasts in temperature and atmospheric conditions that lead to distinct geological features. On the sunlit side, intense heat can cause significant geological activity. Imagine vast, barren plains studded with old lava flows, indicating a history of volcanic eruptions. The constant warmth may lead to the development of expansive deserts where winds sculpt unique rock formations like towering mesas or intricate canyons. Erosion processes on this side are defined by extreme weathering due to heat, leading to a breakdown of rocks into fine dust or sand. Conversely, the dark side of the planet presents an entirely different landscape. With temperatures that are extremely cold, this region may host icy plains and glaciers. Over time, any existing water would freeze, creating a stark, frozen terrain, perhaps with features similar to those found in the deep polar regions of Earth. The lack of sunlight could make this side significantly less geologically active, resulting in a surface marked by ancient impact craters and little erosion from wind or water. The transition zone, or the line between light and dark, known as the Terminator, would be particularly fascinating. Here, varying temperatures could create an environment ripe for geological processes like weathering and sedimentation. The fluctuating conditions may foster the formation of unique landscapes, such as peaks that jut skyward, catching the warm sunlight, while valleys remain perpetually shadowed and cool. Tidal locking shapes geological features fundamentally through its influence on climate and environmental processes, resulting in a planet with diverse and extreme landscapes that reflect the interplay of light and darkness. On a tidally locked world, one side constantly faces its star, while the other remains in perpetual darkness. This unique setup creates strikingly different environments on each side, leading to distinct patterns of wind and heat distribution. Imagine the sunlit side as a vast desert where temperatures can soar, while the dark side becomes an icy expanse with frigid conditions prevailing. The extreme temperature difference between the two sides generates atmospheric movements. Warm air on the sunlit side rises, creating an upward flow that leads to a decrease in pressure. This movement of warm, lighter air contrasts sharply with the denser, colder air on the dark side, which sinks into the atmosphere. The result is a continuous circulation of air between these two very different zones. Winds flow from the cooler dark side toward the heated sunlit side, much like a stream flowing down a slope. This wind system can create powerful atmospheric currents that can vary in intensity depending on the world's specific conditions. The larger the temperature differential, the faster and more vigorous the winds can become, leading to potential storms and turbulent weather patterns primarily located at the edges where the two environments meet. These transitional zones, often referred to as the Terminator line, can be dynamic areas where extreme weather events might emerge due to the clash of warm and cold airs. Additionally, heat distribution doesn't remain confined to the areas directly exposed to sunlight. Some of that warmth can be transported toward the dark side through currents of air and oceanic movements if there are bodies of liquid present. This results in a gradual warming of the dark side over time, although it remains significantly cooler than its sunlit counterpart. A tidally locked world operates under a complex dance between heat and wind, sculpting its weather patterns in unexpected and fascinating ways, creating environments that are as diverse as they are extreme. The term Terminator line refers to the boundary that separates the illuminated side of a planet from the dark side. On Earth, this line can be seen at sunrise and sunset, but on other planets, it plays a significant role in shaping their climate systems. The areas near the Terminator experience unique conditions. Daylight brings warmth, while the dark side remains cold. In planetary climates, this line influences temperature gradients. As the sun's rays strike the planet's surface, they create zones of variable heat, which can lead to dynamic atmospheric movement. Warm air rises and creates low-pressure areas, while cooler air sinks, generating complex weather patterns. This interplay is crucial to understanding how a planet's atmosphere circulates. Take Mars, for example. Its thin atmosphere means that temperatures can change drastically between day and night. The Terminator line marks the edges of these dramatic shifts, impacting factors like dust storms and frost formation. Similarly, on gas giants like Jupiter, the Terminator helps determine cloud formation and storm activity, since sunlight penetrates only halfway through the dense atmosphere, causing distinct weather systems on either side. Researchers study the Terminator line to gain insights into a planet's overall climate dynamics. By analyzing temperature fluctuations, atmospheric pressures, and wind patterns around this boundary, scientists can build better models of how energy distribution happens on a planetary scale. Understanding these systems helps us predict climate behavior and even informs the search for habitable conditions beyond Earth. Tidal locking has profound implications for future colonization or exploration missions to a planet that exhibits this phenomenon. When a celestial body, like a planet or moon, is tidally locked, one side perpetually faces its star, while the other is shrouded in darkness. This creates extreme environmental differences across the surface. On the sunlit side, temperatures could be scorching, making it inhospitable without advanced technologies to shield habitats from intense solar radiation. Conversely, the dark side could plunge into frigid temperatures, likely freezing any water present and making survival extremely challenging. This stark dichotomy necessitates innovative solutions for any colonization efforts, as teams would need to establish colonies that can withstand these extremes. Moreover, the constant sunlight on one side and total darkness on the other could influence energy sources. Solar panels would thrive on the sunlit side, providing abundant energy for activities and habitat maintenance. However, the dark side would require additional energy supply strategies, possibly incorporating nuclear or geothermal energy if the planet has geological activity. Explorations themselves would be affected by this unique feature. Navigating the planet would demand careful planning, with mission schedules needing to account for the long cycle of day and night. Practically, missions might favor the twilight regions, where conditions may be more temperate, allowing for easier exploration and potential settlement. Tidal locking transforms the landscape of a planet, creating unique challenges and opportunities for colonization and exploration. Understanding these dynamics is critical for developing effective strategies, ensuring the safety and sustainability of missions in these environments. Tidal locking is a fascinating phenomenon where a celestial body rotates on its axis in such a way that the same side always faces the object it is orbiting. The most famous example in our solar system is the Moon, which is locked to Earth. However, many other celestial bodies also exhibit this characteristic. One noteworthy example is Pluto, the dwarf planet. Like the Moon with Earth, Pluto is in a state of tidal locking with its largest moon, Charon. This means that as Pluto spins, Charon is always visible from the same point on Pluto's surface. The two bodies also share a unique dance as they orbit a common center of mass located outside either body, creating a fascinating gravitational ballet. Another interesting case involves the moons of the gas giants, such as Jupiter and Saturn. For instance, many of Jupiter's moons, including Io, Europa, and Ganymede, are tidally locked to the planet, meaning they always show the same face to Jupiter. This lock means that one hemisphere of each moon experiences constant daylight, while the other remains in perpetual darkness. Moreover, similar conditions are found among some of Saturn's moons, like Titan. This moon has also reached tidal locking with Saturn, showcasing the gravitational influence the giant planet has on its satellites. Comparing these different celestial bodies, one finds that the size and mass of the primary body exert a significant influence on the relationship. For smaller moons like those of Jupiter, the locking can occur relatively quickly, while the larger bodies, such as Pluto and Charon, exhibit a slower evolution to achieve tidal equilibrium due to their size and distance from each other. Tidal locking reveals much about the history and development of these celestial systems. It acts as a reminder of the interconnected dance in our universe, where gravitational forces shape the physical characteristics of these diverse worlds. The variations among tidally locked bodies highlight the complexity of gravitational relationships in space and provide insights into the evolutionary paths of celestial objects. Tidal locking occurs when an astronomical body has synchronized its rotation period with its orbit around another body. A dramatic illustration of this phenomenon can be seen with moons that are permanently facing their parent planets. By studying extreme examples of tidal locking, scientists have gained valuable insights into how different planetary systems may form and evolve. When we observe a tidally locked moon, for instance, we notice that one side basks in constant daylight while the other remains in perpetual darkness. This extreme variation in conditions can lead to unique atmospheric dynamics. The side in sunlight experiences intense heating, which can create complex weather patterns arising from the stark contrast with the cooler, shadowed side. This effect helps researchers understand how atmospheres might behave on planets orbiting other stars, where similar conditions could be present. Additionally, the phenomenon sheds light on the gravitational interactions between celestial bodies. In systems where one body exerts a significant gravitational influence, it can lead to tidal forces that alter both the rotational and orbital characteristics of nearby objects. These insights into gravitational influences inform our understanding of how planets may be positioned in relation to their stars or companion moons, impacting their capacity to support life. Extreme tidal locking also invites speculation about the potential for habitability in other systems. The dynamics created by locked bodies might allow for stable temperatures on the sunlit side and moderated conditions on the dark side, shaping ecosystems that differ significantly from those on Earth. This broadens the framework for identifying potentially habitable exoplanets, expanding the criteria we might use in searching for life beyond our solar system. Thus, exploring extreme tidal locking not only reveals the unique attributes of specific celestial bodies, but also enriches our knowledge of planetary system dynamics, gravitational interactions, and the potential conditions for life. We learn that the universe is diverse and complex, and many factors contribute to how planets and moons coexist, offering a richer understanding of our cosmic neighborhood. Supervolcanic planets stand out due to their extraordinary capacity for volcanic activity, which can reshape landscapes and influence atmospheres on a massive scale. Unlike smaller volcanic systems found on Earth, supervolcanoes on such planets can produce eruptions that dwarfs typical volcanic activity. Their defining hallmark is the sheer volume of magma and volcanic material they release, which can be thousands of times more than a standard eruption. The intense and consistent volcanic activity on a supervolcanic planet is primarily driven by a combination of internal heat and tectonic dynamics. These planets often possess a significant reservoir of molten rock located beneath the surface. This magma, which remains under immense pressure, can be generated by prolonged cooling of the planet's core or by the decay of radioactive elements, the very same processes that contribute to heat production within the planet. As the molten rock accumulates, it seeks escape routes. Cracks and fissures can form, providing pathways for the magma to migrate towards the surface. When these pathways are obstructed, pressure builds to monumental levels, resulting in explosive eruptions. This cycle of pressure build-up and release creates a rhythm of activity that can seem almost relentless. Additionally, geological features such as calderas, large depressions formed after explosive eruptions, are common on supervolcanic planets, allowing for the collection of erupted material and further volcanic activity. This not only contributes to the planet's geological landscape, but also can alter its atmosphere. Gases released during eruptions create a dynamic environment that can influence climate patterns on a global scale. It is the combination of vast magma reservoirs, intense geothermal heat, tectonic movements, and the ability to build up pressure over time that defines a supervolcanic planet and sustains its intense volcanic activity. The result is a world that, although inhospitable, is alive with the constant reminders of its own inner turmoil. Constant volcanic eruptions can significantly alter the planet's atmosphere and surface, acting as powerful natural phenomena with extensive effects. When a volcano erupts, it releases a variety of gases, including water vapor, carbon dioxide, sulfur dioxide, and ash particles into the atmosphere. These gases can influence climate and weather patterns by creating clouds that block sunlight, leading to cooling effects over time. The ash and other particulates ejected during an eruption can spread over large areas, effectively altering local and regional climates. This can diminish the amount of sunlight reaching the ground, affecting photosynthesis in plants and disrupting ecosystems. Additionally, the sulfur dioxide can convert into fine droplets of sulfuric acid, forming a haze that lasts for years, subtly impacting global temperatures by reflecting sunlight back into space. On the surface of the Earth, volcanic eruptions dramatically reshape landscapes. Lava flows can create new landforms, such as islands or mountains, while the ash fallout can blanket large regions, potentially burying forests and farmland. Over time, the minerals in volcanic materials enrich the soil, which can enhance agricultural productivity in the long run if the immediate destruction causes widespread short-term challenges for those living nearby. Finally, continuous volcanic activity can foster the development of new geological features such as calderas and volcanic craters, contributing to the dynamic nature of the planet's surface. These eruptions serve as a reminder of Earth's powerful internal processes, reminding us of the delicate balance between destruction and renewal in the planet's ever-evolving landscape. Volcanic eruptions vary widely in type and intensity, influenced by many factors, including the composition of the magma, the geologic setting of the volcano, and the physical processes occurring underground. There are several primary eruption styles recognized around the world, each with distinct characteristics. One common type of eruption is the effusive eruption, where lava flows steadily from a volcano. This usually occurs when the magma is low in viscosity, allowing it to flow easily. Hawaiian volcanoes exemplify this style, producing long-lasting river-like lava flows and spectacular lava fountains. The intensity of these eruptions tends to be lower, presenting fewer immediate dangers to surrounding areas. Contrasting this is the explosive eruption, marked by violent energy release. Explosive eruptions occur when magma is thick and gas-rich, preventing gases from escaping easily. This creates immense pressure that eventually results in powerful explosions. Mount St. Helens in the United States is well known for such eruptions, with ash clouds and pyroclastic flows that can devastate nearby landscapes. There are also intermediate types, such as strombolian eruptions, which produce bursts of lava and gas that eject into the atmosphere but are less destructive than the more explosive varieties. These eruptions are seen at volcanoes like Stromboli in Italy, where regular rhythmic explosions occur. The intensity of volcanic eruptions can be described on a scale that considers various parameters, such as the volume of eruptive material, the height of the eruption column, and the duration of the event. For example, a highly explosive eruption might yield vast amounts of ash that can spread over hundreds of kilometers, while a quieter effusive eruption may contribute to gradual land formation. Geographically, volcanic regions fall primarily along tectonic plate boundaries or over hotspots. Subduction zones, where one plate moves under another, often give rise to more explosive eruptions due to the accumulation of more viscous magma. In contrast, mid-ocean ridges and hotspots typically result in more effusive activities. Ultimately, the variations in eruption types and intensities reflect the complex interactions among volcanic materials, the environment, and the geological processes at play. Understanding these differences not only provides insight into the volcanic landscape, but also informs safety measures for communities living in proximity to active volcanoes. Volcanic activity in space can reveal fascinating similarities and stark contrasts to Earth's geological history. While Earth experiences tectonic shifts and volcanic eruptions driven by a dynamic crust floating on a molten mantle, many celestial bodies exhibit their own unique volcanic phenomena influenced by different conditions. For instance, on Earth, the movement of tectonic plates can lead to volcanic eruptions along plate boundaries. This geological dance creates diverse volcanic landscapes and eruption styles. In contrast, volcanic activity on other planets, such as Mars or Venus, can be driven by factors like the planet's size, atmospheric pressure, and heat retention. Mars, for example, hosts massive shield volcanoes shaped by persistent lava flows, indicating a potentially different eruption mechanism than what we typically observe on Earth. Moreover, some moons in our solar system, like Io, one of Jupiter's moons, showcase volcanic activity that is not only frequent but also extremely intense. Io's eruptions are fueled by tidal heating caused by gravitational interactions with Jupiter and other moons, leading to a much different environment for volcanism compared to Earth, where gravity dictates lava flow and eruption patterns. While both Earth and other celestial bodies illustrate energetic geological processes, the underlying mechanisms and the resultant volcanic formations can vary greatly. Thus, the study of these extraterrestrial volcanoes not only enhances our understanding of their own geological histories, but also sheds light on the broader dynamics of planetary formation and evolution across the universe. The interplay of various forces creates a complex tapestry of volcanic activity in space, echoing yet diverging from the story told by Earth's own volcanic past. Studying explosive volcanic environments from a distance requires a suite of advanced instruments that can capture various aspects of these dynamic systems without putting researchers in harm's way. Satellite imagery plays a crucial role, providing broad coverage of volcanic regions and allowing scientists to monitor changes in landforms, thermal emissions, and ash dispersal patterns from space. These instruments can detect heat, giving insight into a volcano's activity level, as warm spots often indicate rising magma. Ground-based remote sensing is another vital tool. Techniques such as laser altimetry help map the topography of volcanoes with remarkable detail, revealing changes in elevation and surface deformation that can signal an impending eruption. Radar systems can penetrate cloud cover, measuring ground movement and detecting volcanic gases that might escape the surface, vital for assessing eruptions' potential risks. Additionally, weather balloons equipped with gas sampling instruments can ascend into the atmosphere, collecting data on volcanic gases like sulfur dioxide, which can indicate activity levels. Acoustic sensors play an important role too, as they can capture the sounds generated by volcanic eruptions, helping to determine their intensity and frequency. By deploying a combination of these techniques, researchers can build a comprehensive picture of volcanic behavior, enabling timely warnings and better understanding of the volatile environments these natural wonders inhabit. The synergy of satellite technology, ground-based observation, and in-the-field instrumentation provides a multifaceted approach, essential for unraveling the complex nature of explosive volcanoes. The volcanic landscape represents a unique geological tapestry where extraordinary minerals and compounds can form. When a volcano erupts, it releases a variety of materials, including magma, gases, and ash. As the magma cools and solidifies, it can create a fascinating array of mineral crystals. These conditions are prime for the formation of uncommon minerals that might not appear in more stable environments. Volcanic activity also alters existing rock formations, leading to processes like hydrothermal alteration. Hot fluids can permeate through cracks in the rock, reacting with the minerals present and forming new compounds unique to that environment. This process is essential in creating mineral deposits rich in resources like copper and gold, as well as rare earth elements crucial for modern technology. Moreover, the specific chemical composition of the erupted materials varies greatly depending on the type of volcano and the tectonic circumstances surrounding it. This diversity adds another layer of complexity to the mineral landscape. For instance, one volcano might produce obsidian, which has a glassy texture, while another creates pumice, full of air pockets and lighter in weight. The temperatures generated by volcanism can also facilitate the emergence of unusual compounds that require extreme conditions to form. For example, some minerals may remain stable only under high temperature and pressure, conditions that are readily available in volcanic regions. Additionally, the presence of volcanic gases, like sulfur dioxide, can lead to the formation of sulfide minerals, which are often rare and highly sought after for industrial applications. Exploring volcanic areas can reveal an incredible wealth of mineralogical diversity. From brightly colored crystals to sturdy metallic ores, the landscape serves as a natural laboratory for geologists and mineralogists, continuously shaping and redefining our understanding of Earth's richness. Each volcanic eruption has the potential to expose something previously hidden, making these regions hotbeds for mineral discovery and scientific inquiry. Sending a mission to a volatile planet presents a thrilling combination of potential risks and rewards that can reshape our understanding of the universe. On one hand, the rewards are substantial. Each mission could uncover new knowledge about the planet's atmosphere, geology, and possibly even its history. Such discoveries might reveal clues about how planets evolve, which can inform our understanding of Earth and other celestial bodies. Furthermore, insights gained could enhance our ability to protect our own planet from cosmic threats or inform strategies for future colonization efforts. Conversely, the risks involved are significant. Volatile planets, characterized by extreme temperatures, fierce storms, and erratic geological activity, can present life-threatening challenges to both equipment and personnel. For instance, the intense atmospheric conditions can damage spacecraft, making it difficult to gather data or even safely land. There is also the possibility of encountering high levels of radiation or volcanic activity, which makes prolonged missions incredibly perilous. The mission could also be compromised by unforeseen events, such as equipment failure or environmental hazards, leading to loss of precious scientific instruments, or even the mission itself. Ultimately, while the mission to a volatile planet carries considerable dangers, the potential to expand our scientific horizons and deepen our comprehension of the cosmos may outweigh these challenges. Each foray into the unknown not only fuels our curiosity, but also lays the groundwork for advancements in technology and understanding that can benefit humanity as a whole. To understand why some planetary bodies exhibit intense volcanic activity, scientists look deep beneath the surface to explore their internal structures. A planet's internal composition and the processes occurring within can greatly influence its volcanic behavior. At the core, many planets, including Earth, are thought to have a dense metallic center surrounded by a layer of molten rock known as the mantle. This mantle is not static, it is active and convective. Picture a pot of boiling water. Heat from the bottom causes the water to churn and circulate. Similarly, the heat generated by a planet's core causes the mantle rock to rise and fall, producing convection currents. These currents can generate significant pressure in certain areas, leading to the melting of materials in the mantle. When enough magma forms, it can rise towards the surface. If there's a pathway available, this molten rock can escape, resulting in volcanic eruptions. Also, not all planets experience volcanic activity the same way. For example, some planets, like Venus, showcase enormous volcanic plains and shield volcanoes, suggesting they have been subjected to sustained geological activity over millions of years. This endurance may be due to a thicker atmosphere and different pressure conditions that allow the constant generation of magma. In conclusion, scientists theorize that the intense volcanic activity observed on certain planets is a result of ongoing heat from their cores, dynamic mantle convection, and unique surface pressures that allow magma to easily reach the surface, providing insights into the fascinating geological processes at play within these celestial bodies. In the vast cosmos, the potential for life is more extensive than many of us might assume. Extremophilic organisms, those that thrive in extreme conditions on Earth, offer a glimpse into this possibility. These remarkable life forms can be found in the most inhospitable environments, such as boiling hot springs, deeply frozen ice, or the acidic depths of oceans. Their existence raises intriguing questions about survival in alien environments, possibly resembling those found on other planets or moons. For instance, the icy crust of Europa, one of Jupiter's moons, harbors an ocean beneath its surface. This environment could potentially support life similar to extremophiles on Earth, as the subsurface ocean may contain the necessary chemical ingredients, along with warmth generated through tidal heating from gravitational interactions with Jupiter. Such a setting could create a rich habitat for microbial life, feeding on the chemical energy available in its surroundings. Similarly, Mars presents a captivating case for the potential of life. While its surface conditions are harsh, thin atmosphere, extreme cold, and radiation, the discovery of ancient riverbeds and minerals suggesting past water raises the prospect of simpler life forms possibly surviving beneath the surface, where conditions are more stable and protective. Then there's Enceladus, another of Saturn's moons, which has plumes of water vapor erupting from its surface. Studies of these geysers indicate that they contain organic compounds, hinting at a subsurface ocean. These conditions could be ripe for organisms that feed on available chemicals, much like those found around Earth's hydrothermal vents. The possibilities are not limited to just these examples. Whether considering tidally heated worlds, subterranean lakes, or even the thick atmospheres of gas giants where clouds may harbor microbial life, the adaptability of extremophiles is a powerful reminder that life might find a way in the universe's most extreme habitats. This adaptability gives scientists hope that we may someday discover living organisms in places beyond our wildest imaginings. Volcanic activity on a planet can be a window into the past, revealing the processes that shaped it during its formative years. When a planet has active volcanoes, it indicates that heat is being generated within its interior, likely from the same processes that occurred when the planet was first forming. In those early stages, the planet was a chaotic environment where immense heat and pressure led to the melting of minerals and the eventual separation of materials by density. This resulted in a core, mantle, and crust similar to what we see in many terrestrial planets today. The types of volcanic eruptions and the materials they produce can tell us about a planet's composition and the conditions present when it was formed. For instance, if a planet ejects certain gases and minerals like sulfur and carbon dioxide, it may imply a history of volcanic activity that reflects the original ingredients of the planet while providing clues about its development. Furthermore, studying the chemical signatures of volcanic rocks can show how the planet's crust evolved over time, providing a record of historical events like the cooling of lava and the formation of surface features. Volcanic activity can also reveal the dynamics of a planet's mantle, the layer beneath the crust. Understanding how magma moves and interacts with the crust gives researchers essential information about thermal gradients and the mechanisms driving tectonic processes. Such insights help scientists construct models of planetary evolution, allowing comparisons with other planets and moons, including Earth, which can deepen our understanding of planetary systems across the universe. By examining the history and patterns of volcanic eruptions, scientists gain invaluable insights that inform our knowledge about planetary formation processes, offering a narrative of a planet's journey from a molten mass to the complex worlds we explore today. The planet renowned for its dark, hypnotic storms is Neptune. These storms, often appearing as vivid blue hues against the planet's deep atmosphere, manifest in a unique way due to Neptune's frigid environment. Unlike the warm, turbulent storms we see on Earth, Neptune's storms are influenced by its extreme cold and high-pressure atmosphere. On this distant world, powerful winds can reach astonishing speeds, stirring up clouds of methane and generating massive storms that can last for long periods. The extremely low temperatures create conditions that allow gases to condense into ice particles, contributing to the characteristic shimmering, swirling patterns of the storms. When these storms erupt, they can produce dark vortices, which are akin to hurricanes but exhibit striking distinctions in their composition and structure. These storms, with their intricate dynamics, reflect an ongoing interplay of wind patterns and thermal contrasts, showcasing the complexity of atmospheric behavior even in a frozen realm. On Neptune, the storms stand as a testament to nature's ability to create phenomena that are as captivating as they are mysterious. Cold conditions on a planet play a crucial role in shaping its storm patterns, particularly in regions where temperatures are significantly low. To understand this, think of the atmosphere as a giant ocean of air, where temperature differences create movement. In colder areas, the air pressure typically increases, leading to denser, heavier air. Conversely, warmer air, which can hold more moisture, rises and creates a system of low pressure. When these contrasting temperatures interact, the cold air can push underneath the warmer air, leading to the formation of strong winds. This process is similar to how waves form on the surface of water, where energy and movement create visible changes. As a result, you can see spiraling clouds, intense winds, and sometimes even violent weather patterns as these air masses collide. Moreover, cold conditions can enhance the ability of storms to retain moisture. When warm air rises, it cools, and the water vapor it carries condenses into clouds. This can lead to heavy precipitation. On a planet with significantly cold temperatures, the extreme differentials can also lead to unique types of storms that have characteristics not commonly seen on warmer planets. In places like the polar regions, the stability provided by cold, dense air can sometimes trap moisture and create persistent storm systems, which can evolve into gigantic blizzards or other powerful weather events. These distinctive storms are heavily influenced by the cold environment, combining the intensity of cold air with the dynamics of wind and moisture, resulting in some of the galaxy's most mesmerizing and formidable atmospheric phenomena. The captivating dark appearances of storms, particularly those on planets like Jupiter or Earth, stem from a combination of atmospheric phenomena. At the heart of these storms, towering clouds form due to powerful updrafts that carry warm, moist air upwards. As this air rises, it cools and condenses, creating dense cloud layers. Within these clouds, droplets of water or ice reflect and scatter sunlight, giving the cloud tops a bright appearance. However, as we look deeper into the storm, the clouds become thicker and denser, blocking the sunlight from penetrating further. This thick cloud cover can lead to a stark contrast, where the exposed, lighter tops stand out against the deep shadows created below. Additionally, storms can be home to intense energy and turbulence. This energy can lead to dynamic changes in temperature and pressure, causing the clouds to shift rapidly. Such movements can create darker regions within the storm, as the denser areas cast shadows while simultaneously allowing lighter zones to reflect light, creating a mesmerizing interplay of brightness and darkness. Furthermore, the presence of specific chemicals and particles can alter the color and appearance of storm clouds. In some giant gas planets, for example, abundant ammonia and other compounds can lend a characteristic tint to clouds, contributing to their captivating visuals. The interplay of these elements creates a spectacle that can be both beautiful and foreboding, reflecting the immense forces at work within these storms. On this frozen planet, the storms exhibit characteristics that are both fascinating and extreme, particularly when compared to other weather phenomena in the vast expanse of space. Imagine a world where fierce winds whip across icy landscapes, creating snow and blizzard-like conditions that can last for days. These storms are driven by the planet's unique atmospheric conditions, including its low temperatures and high levels of wind shear, which can propel gusts fast enough to reshape the surface. When we compare these storms to others in the solar system, the scale becomes mind-boggling. Consider the raging storms of Jupiter, where enormous cyclones swirl over vast areas much larger than Earth itself. These storms can persist for centuries, fueled by the gas giant's constant supply of energy from deep within its atmosphere. Similar to our frozen planet, these storms exhibit violent winds and are often accompanied by swirling clouds, but the sheer size and duration of Jupiter's atmospheric upheavals dwarf those of icy worlds. Another comparison can be made with the dust storms on Mars, which develop more sporadically but can envelop the entire planet. These storms can last for weeks and reflect a different type of extremity, as they arise from the planet's thin atmosphere and can influence temperature shifts across vast distances. Whereas the frozen planet's storms create a stark contrast between icy precipitation and swirling snow, Mars experiences intense conditions without the presence of liquid water. Even further afield, we look at the extreme winds on Neptune, where the atmosphere delivers some of the fastest winds recorded in the solar system. Neptune's storms are more tempestuous and fleeting, showcasing the dynamic nature of weather in the outer reaches of our solar neighborhood. However, they mostly encompass gas and clouds rather than icy precipitation. Storms on this frozen planet are remarkable in their own right, presenting unique challenges and effects influenced by low temperatures and wind patterns. While they may not match the scale of Jupiter's colossal storms or the duration of Martian dust clouds, they illustrate the diverse phenomena that make up space weather and highlight how each planetary environment shapes its atmospheric behaviors distinctly. Astronomers employ a variety of techniques to study the visually striking storms that occur on planets, especially in our solar system. One of the primary methods is through the use of powerful telescopes equipped with advanced imaging technology. Ground-based observatories and space telescopes capture detailed photographs of these storms, allowing scientists to observe their formation, movement, and evolution over time. In addition to visual observations, astronomers utilize spectrometry, which involves analyzing the light emitted or absorbed by the storms. By studying the spectrum, or the range of different colors of light, they can identify the chemical composition and physical conditions within these storms. This method reveals important information about what fuels the storms and helps to understand their energy sources. Space missions bring another essential tool to the study of atmospheric phenomena. Probes equipped with instruments can fly directly through or orbit around storm systems, collecting data on temperature, pressure, and gas compositions. This direct analysis provides ground truth data that complements distant observations. Computer simulations and modeling also play a crucial role. By inputting data gathered from telescopes and missions, scientists can create models to predict storm behavior and responses to various atmospheric conditions. This helps shed light on processes that are otherwise too intricate to study through observation alone. Moreover, astronomers analyze historical data from previous observations. By comparing current storms to documented ones from years past, they can identify patterns and changes over time. This longitudinal approach helps in recognizing how storm systems evolve, intensify, or dissipate. Together, these diverse techniques provide a comprehensive understanding of these stunning atmospheric phenomena, allowing astronomers to piece together the intricate puzzle of storm dynamics beyond our home planet. In the frigid environment of outer space, how storms behave can be quite different from what we experience on our planet. When considering storms on distant celestial bodies, the extreme cold plays a crucial role in their formation and longevity. The low temperatures can lead to unique physical processes that limit the energy available for these storms to develop. For example, on Saturn, the surrounding atmosphere is incredibly cold, allowing clouds to form from ammonia and water. In such temperatures, chemical reactions occur at a different pace, making them slower. As a result, storms can persist for longer periods. Without the heat of the sun's warmth, these storms often become more stable, taking on lasting characteristics that allow meteorological phenomena like the Great White Spot to swirl on for extended durations. Additionally, the presence of ice and frozen gases can affect the density and structure of storm clouds. Conditions can lead to thicker, more robust formations that enhance their strength. When winds swirl through these frigid environments, they can move more slowly, allowing storms to dissipate more gradually than they would in warmer climes, where turbulence and evaporation can bring about a quick end. The freezing surroundings foster a different set of rules for how storms act. By altering chemical processes and atmospheric dynamics, the intense cold not only modifies their lifespan, but transforms their very nature, leading scientists to continuously marvel at these otherworldly weather patterns. The storms observed on a planet can often be intricately linked to its magnetic and polar regions. To understand this connection, consider the planet's magnetic field as an invisible shield shaped by the movement of charged particles within the planet's core. This magnetic field channels energy and affects the behavior of atmospheric phenomena. In regions near the poles, where the magnetic field is typically more concentrated, storms can exhibit heightened activity. The magnetic field interacts with solar winds, streams of charged particles emitted by the sun, which can lead to the creation of spectacular auroras. These visual displays are the result of charged particles colliding with atmospheric gases, releasing energy in the form of light. Enhanced storm activity in these areas can often occur simultaneously, as the influx of energy from solar winds invigorates the atmosphere, stirring up weather patterns. Moreover, storms can influence and be influenced by the thermal dynamics of the polar regions. For instance, if a storm generates significant heat, it can alter atmospheric pressure and flow patterns, which may, in turn, push the boundaries of polar climates. Such dynamics may lead to shifts in ice coverage, impacting both the planet's albedo, its reflectivity, and its overall climate systems. Ultimately, the interplay between a planet's magnetic field, polar regions, and storm systems creates a complex web of interactions, resulting in diverse and sometimes extreme weather phenomena. Understanding this connection enriches our knowledge of planetary atmospheres and the forces that shape them, whether here on Earth or on other worlds exploring the cosmos. Intense storms, particularly in planetary atmospheres, create an environment that is rich in dynamic interactions and extreme conditions. These violent weather patterns have the potential to become natural laboratories for studying atmospheric science and particle physics. When storms unleash their fury, they propel particles through the atmosphere at rapid speeds and create fascinating phenomena. One significant opportunity presented by storms lies in their ability to generate electric fields. As winds howling through the atmosphere collide with various particles, they can tear electrons from molecules and create plasma. This plasma is a soup of charged particles that significantly alters the local physics. Understanding how these electric fields work and how they interact with particles can lead to insights about energy transfer mechanisms and the creation of new compounds that may not form under calmer conditions. Moreover, storms can influence large-scale circulation patterns, which in turn affect cloud formation and precipitation. Scientists can study how humidity, temperature variations, and other factors play into storm development, leading to deeper understanding of climate systems. For particle science, intense storms might produce high-energy events like lightning strikes, which are known to generate gamma rays. These emissions serve as intriguing subjects for researchers studying cosmic rays and other high-energy particles, potentially revealing new information about their origins and behavior. Additionally, the turbulence and chaos within storms can stir up aerosols and trace gases from the surface, lifting them into the upper atmosphere. This mixing process allows scientists to track the transport of pollutants and biological materials, providing insight into their roles in climate change and atmospheric chemistry. By analyzing samples collected during or after these storms, researchers can identify changes in atmospheric composition, which can have profound implications for understanding global weather patterns. The violent dynamics of intense storms unveil a multitude of opportunities, ranging from investigating the mechanics of particle interaction to exploring the intricate workings of our atmosphere. Each storm tells a story of energy, chaos, and transformation, offering a unique glimpse into the forces that shape our planet and the universe beyond. The discovery of a new planet can ignite a variety of myths and cultural interpretations shaped by human imagination and experience. Imagine a vibrant world that appears different from our own. Its unique features, such as swirling storms, unusual colors, or seemingly alien landscapes, could provoke stories of its origins. Cultures may envision the planet as a divine being or an otherworldly realm, drawing parallels to the gods and cosmic entities from their narratives. For instance, a planet with an intense atmosphere might be seen as a place of wrath and chaos, serving as a cautionary tale about hubris or disobedience. In contrast, a serene and idyllic planet could symbolize hope and abundance, inspiring tales of a utopian paradise where all beings coexist in harmony. These interpretations could reflect humanity's own struggles and aspirations, serving as a mirror to societal values and fears. Different cultures might invent stories about the inhabitants of such a planet. Some may envision advanced civilizations with extraordinary technologies, acting as guardians of ancient wisdom. Others could see the planet as a sanctuary for mystical creatures, representing our dreams of escape from the trials of daily life. The characteristics of the planet, such as its position in the solar system or alignment with certain celestial events, could further influence the myths, leading to beliefs that tie the planet's fate to human destiny. Moreover, the arrival of new astronomical discoveries often leads to a resurgence in spiritual and philosophical discussions. Communities might hold a new reverence for the cosmos, resulting in rituals or celebrations driven by curiosity about our place in the universe. Thus, observing such a planet can inspire a rich tapestry of mythology, culture, and reflection, reminding us of our innate desire to understand the mysterious forces that shape our existence. The study of storms in our solar system, particularly those on gas giants like Jupiter and Saturn, provides fascinating insights that challenge our current understanding of weather dynamics beyond Earth. Traditionally, we associate weather phenomena with influences that are relatively familiar, like solar radiation and atmospheric composition. However, the massive storms observed on these planets, with their immense size and longevity, prompt scientists to rethink several aspects of atmospheric science. For instance, the Great Red Spot on Jupiter is a colossal storm that has been raging for at least a few hundred years, possibly much longer. Its persistence and scale defy expectations based on terrestrial weather patterns, which are typically temporary and much smaller in scope. This raises questions about how energy and materials are mixed within such vast systems and what underlying processes keep these storms active over such extended periods. Moreover, the dynamics of these storms are influenced by the deep atmospheres of gas giants, where pressure, temperature, and composition could behave very differently than what we observe on Earth. Scientists are increasingly realizing that factors like internal heat, derived from the planet's formation process rather than solar radiation, play a significant role in driving these massive weather systems. This contrasts with the conventional understanding of weather, which primarily attributes storm formation to solar heating. As researchers use advanced telescopes and spacecraft to study these storms in detail, they are discovering that the interactions between different atmospheric layers can lead to unexpected behaviors. For instance, the way winds flow at enormous speeds and the role of ammonia and other compounds in the atmosphere contribute to a complex system that challenges simplified models of atmospheric circulation. What's truly captivating is the notion that these insights could enhance our understanding not just of other planets, but of our own climate system as well. The challenges presented by extraterrestrial storms offer a broader perspective, prompting scientists to reevaluate existing theories about atmospheric dynamics and potentially apply new findings to Earth's ever-changing climate. Thus, the study of storms across the solar system reveals a dynamic interplay of factors that continually reshapes our understanding of weather and atmosphere. The ocean world is a captivating yet eerie concept in the context of space exploration, primarily because of its deep, dark expanses that seem ripe for mystery and fear. Imagine an ocean that stretches endlessly beneath a thick atmosphere where the pressure increases dramatically as you descend. This crushing pressure can be frightening in its own right, creating an environment that is deadly to most known life forms. As one goes deeper, light fades into near-complete darkness, giving way to an alien landscape that is void of familiar cues, which can evoke a sense of unease. Additionally, the ocean depths could house unknown creatures that have adapted to the extreme conditions, echoing the horror tropes of the deep sea on Earth. These creatures, hidden in the shadows and potentially bioluminescent, could inspire fascination and fear, suggesting life forms that operate outside our comprehension. The unfamiliarity of these environments provokes questions about what might exist there, feeding into the horror narrative surrounding the unknown. Moreover, the idea of isolation in such vast depths is another layer of this horror. An astronaut or explorer submerged in an alien ocean may experience not only the physical peril of the crushing water, but also a psychological toll from the profound solitude. This theme of isolation is prevalent in horror genres, creating fear through a combination of dread for physical safety and the existential weight of being utterly alone in an uncharted world. As the exploration of these ocean worlds advances, the potential for discovering bizarre and unsettling phenomena only adds to the horror. Every dark corner of an alien ocean could conceal not just mysteries, but threats, making them a focal point for imagination and caution alike. These elements together intertwine to create a powerful narrative of fear, wonder, and the unknown in the depths of space. The pressures found at the depths of the ocean on other celestial bodies are strikingly different from those experienced in Earth's own oceans. To understand this, consider the weight of water above you. In Earth's oceans, the pressure increases as you descend, owing to the immense volume of seawater. Each layer of water exerts its weight on the layers below, resulting in pressure that builds steadily with depth. Now, if we shift our perspective to the depths of oceans found on distant moons or planets, we encounter fascinating variations. For instance, take one of Jupiter's moons, Europa, which is covered by a thick shell of ice over a subsurface ocean. The pressure there, while potentially extreme, is shaped by the unique characteristics of its icy surface and the volume of water beneath. The conditions can be drastically different from Earth's environments, especially when considering temperature and the compositions of the water. On the other hand, the pressures that may exist on Titan, Saturn's largest moon, increase sharply due to its dense atmosphere and the thick layers of liquid methane and ethane on its surface. Here, the pressure can be significantly higher than that in Earth's oceans, which is partly due to the dense atmosphere exerting additional weight. Overall, while Earth's ocean depths experience pressure-driven increases mainly from the weight of water, the pressures on other celestial bodies are influenced by various factors, including atmospheric conditions, the composition of the liquid beneath, and the unique gravitational effects of those moons or planets. Each environment tells its own story, shaped by gravitational forces, fluid dynamics, and the very nature of the materials involved. The deepest parts of the Earth's oceans are a realm of mystery and wonder, a world that few have ever seen. Picture an environment so dark that light from the sun never reaches it. This deep ocean, known as the abyss, is an alien landscape filled with extraordinary creatures that have adapted to survive under extreme conditions. Immense pressure, frigid temperatures, and complete darkness. Here, bioluminescence reigns supreme. Some animals, like certain species of jellyfish and deep-sea fish, generate their own light through chemical reactions. This ability not only helps them find mates in the pitch-black waters, but also serves as a lure to attract unsuspecting prey. Other organisms use their glow for self-defense, creating a dazzling distraction that allows them to escape predators. The strange life forms of the deep also include bizarre adaptations, such as gigantic squid with long trailing tentacles and fish with oversized mouths designed to swallow prey in one swift motion. Predators and prey often bear elongated bodies or transparent skin, features that are beneficial for both hunting and evading capture in such a harsh environment. Venturing even deeper, we encounter hydrothermal vents, which are openings in the ocean floor that spew out superheated water rich in minerals. Here, a unique ecosystem thrives, powered not by sunlight, but by chemosynthesis, a process where organisms, such as giant tube worms and extremophilic bacteria, convert chemical energy into food. This extraordinary community showcases how life can flourish in places once thought uninhabitable, pushing the boundaries of our understanding of biology. As scientists continue to explore these depths, they often stumble upon new species and entire ecosystems that challenge existing notions of life on Earth. What could be lurking in these shadowy waters? Each discovery reveals that the ocean's depths are not desolate, but rather vibrant with life forms, many of which remain unknown to us, waiting to be studied and understood. The mysteries of the deep ocean remind us of the vastness of our planet and the unexplored worlds that lie beneath the waves. Developing vehicles and technologies capable of withstanding intense pressures is a significant challenge in the realm of space exploration. To grasp this, consider the immense forces encountered in extreme environments, such as the deep ocean or the surfaces of other celestial bodies. The first step in creating suitable technology involves understanding the specific conditions these vehicles will face, including temperature changes, radiation levels, and, importantly, pressure variations. Materials play a pivotal role in this endeavor. Scientists and engineers invest considerable efforts into identifying and designing specialized materials that can endure high pressures without deforming. For instance, certain metals combined with composites can provide strength while remaining lightweight. This is crucial because every extra ounce requires more fuel, impacting the overall efficiency of the mission. Next, structural design is key. Engineers employ advanced techniques like computer modeling to simulate conditions that vehicles will face. This allows for the optimization of shapes and forms that can efficiently distribute stress when under pressure. Rather than adopting conventional designs, innovative approaches such as spherical or cylindrical shapes are often utilized since these forms reduce weaknesses and resist crushing forces more effectively. Moreover, rigorous testing is essential to ensure reliability. Vehicles are subjected to simulations that mimic extreme conditions found in space or on planetary surfaces. These tests help to identify weaknesses and allow for adjustments before any real-world application. In this preparation phase, the aim is to ensure that when the time comes for exploration, the technology is proven and capable of handling the challenges of the environment. Finally, the integration of redundant systems into vehicle design enhances safety. Redundancy means having backup systems that can take over if primary ones fail, providing an additional layer of security during exploration. This is especially important when missions venture into uncharted territories where the risk levels are higher. The development of pressure-resistant vehicles for exploration relies on an intricate combination of advanced materials, innovative design strategies, extensive testing, and robust safety measures. Together, these elements craft the tools needed to explore the unknown frontiers of our universe while ensuring that human ingenuity can withstand the harshest of conditions. Detecting thermal vents and other features on the ocean floor is crucial for several reasons, both scientific and ecological. Thermal vents, often found along mid-ocean ridges, release superheated water rich in minerals from beneath the Earth's crust. This process reveals the dynamic nature of our planet's geology, showcasing the interaction between the ocean and the Earth's interior. Such features also contribute valuable information about tectonic plate movements, which are fundamental to understanding how our planet is shaped over time. Moreover, these vents support unique ecosystems teeming with life that thrive in extreme conditions. Unlike most organisms that rely on sunlight, the life forms near thermal vents depend on chemosynthesis, converting chemicals released by the vents into energy. This discovery challenges traditional ideas about ecosystems and where life can exist, suggesting that similar habitats might exist on other planets or moons in our solar system, such as Europa or Enceladus, which have subsurface oceans. Additionally, studying these features allows scientists to explore the origins of life on Earth. The extreme conditions of thermal vents could resemble those of early Earth, where life is believed to have first emerged. By understanding the biological and chemical processes occurring in these unique environments, researchers can gather insights into the fundamental requirements for life, shaping our theories about the potential for life elsewhere in the universe. The significance of detecting thermal vents lies in their ability to enhance our understanding of Earth's geology, ecological systems, and the origins of life, while also providing a gateway to explore extraterrestrial possibilities. Beneath the ocean's surface, complex currents and dynamics play a crucial role in regulating the Earth's climate and ecosystems. Imagine the ocean as a vast, layered system, where warm and cold water mingle, creating movement in a dance of energy. At the surface, winds drive currents that can stretch for thousands of miles. These currents, like rivers in the ocean, transport warm water poleward and cold water toward the equator, influencing weather patterns and climate significantly. However, beneath the surface, a different set of currents known as thermohaline circulation takes over. This process is driven by differences in water temperature and salinity, basically how salty the water is. When water in certain areas becomes colder or saltier, it becomes denser, causing it to sink. This sinking water initiates a global conveyor belt-like movement. Essentially, as colder, denser water sinks, warmer water rises to take its place, creating a complex flow system that can take decades to complete a full cycle. These dynamics not only help distribute heat across the planet, maintaining more balanced climates, but they also play a critical role in nutrient cycling within the ocean, supporting thriving marine ecosystems. Moreover, underwater topography such as ridges, mountains, and seafloors influences these currents as well. Just like wind redirected by mountains, ocean currents bounce off these underwater features, creating eddies and whirlpools. These features enhance mixing, distributing nutrients from the depths to the surface, which are vital for marine life. The interplay of these currents and ocean dynamics is intricate and essential, shaping not only ocean health but also affecting weather systems far beyond the coastal areas, reminding us that the ocean is far more than a static body of water. It is an active, vibrant contributor to Earth's life support systems. Understanding ocean worlds, especially those like Europa, Enceladus, or even distant exoplanets with vast oceans beneath icy crusts, significantly transforms our perspective on the potential for aquatic life in space. These environments, which are rich in water, have been shown to host the conditions necessary for life as we know it. Imagine an ocean world that has a thick layer of ice covering an expansive ocean. Below that ice, geothermal activity can create warmth, providing energy comparable to what we find in Earth's deep-sea hydrothermal vents, locations where life thrives despite the absence of sunlight. This realization opens up the possibility that life might not only exist under similar conditions on these distant worlds, but could be diverse and complex. Moreover, the chemistry of these oceans is crucial. Just as Earth's oceans are full of nutrients and organic materials fostering a rich ecosystem, scientists speculate that the water in these extraterrestrial worlds could contain the essential elements required for biochemical processes. This suggests that life, if it exists in such environments, may utilize processes similar to those seen in Earth's aquatic organisms, despite being isolated from the sun's energy. The implications of such possibilities push us to rethink where life could thrive beyond Earth. If aquatic ecosystems can flourish in icy, dark, and distant locations, then the search for life could extend far beyond just Earth-like planets orbiting stars at a similar distance to our Sun. This expands our understanding of habitability, suggesting that life may come in forms and exist in environments far more varied than previously imagined. The ocean worlds offer tantalizing clues that life could be resilient, adaptive, and possibly widespread throughout the cosmos. The crushing depths of a planet, much like those found in oceanic trenches or beneath thick layers of crust, exert tremendous pressure that significantly influences its geology and tectonic activity. Imagine the weight of countless layers of rock pressing down on a solid foundation. This immense pressure alters the state of materials found deep within the Earth's crust and mantle, resulting in complex geological processes. At these depths, temperatures increase, causing rocks to become more ductile, meaning they can flow rather than break. This flowing rock can lead to the formation of magma, which might eventually rise and contribute to volcanic activity at the surface. The immense pressure also affects the behavior of tectonic plates. As plates move, they can become trapped at fault lines. When the stress exceeds the strength of the rocks, it can cause sudden slips, resulting in earthquakes. Deep within the Earth, the movement of tectonic plates is crucial for recycling materials. Subduction zones, where one plate slides beneath another, create deep trenches. These zones are essential for transforming surface rocks into new materials, which are then brought back to the surface through volcanic activity. Furthermore, the dynamics of deep Earth processes like convection currents in the mantle create zones of uplift and subsidence that shape the landscape over time. The interaction between gravity, pressure, and temperature at these crushing depths drives the ongoing evolution of the planet's geology, making it a rich tapestry of ever-changing features. Overall, these deep, pressing forces not only affect the immediate geological activity, but also play a pivotal role in the long-term transformation of the planet's structure. Adapting to life in extreme environments, such as those found on other planets or moons, could indeed spark significant technological advancements here on Earth. When scientists and engineers are faced with the challenges of survival in harsh conditions, think extreme temperatures, high radiation, or low gravity, they are pushed to innovate and create solutions that can address these issues. For example, developing life support systems that provide breathable air and clean water in places with minimal resources could improve emergency response technologies and sustainability efforts in disaster-prone areas on Earth. Similarly, materials crafted to withstand the intense conditions of space may lead to stronger, lighter materials used in architecture and transportation. Moreover, the methods devised for efficient energy production or waste recycling in space habitats could inspire greener technologies that minimize environmental impact back home. Innovations in robotics and artificial intelligence, driven by the need to explore distant lands without human presence, might also enhance automated systems used in agriculture, manufacturing, and healthcare. The importance of adaptability and resilience in space exploration not only develops our understanding of life beyond Earth, but also paves the way for progress that directly benefits life on our planet, illustrating how the exploration of the cosmos can have profound implications for terrestrial technology and quality of life. Earth's oceans are unique, yet intriguing comparisons can be made with other bodies within our solar system. Our planet's oceans are teeming with life and play a crucial role in regulating climate, contributing to weather patterns, and sustaining ecosystems. Their vastness also serves as a prime example of how liquid water is essential for life as we know it. When we turn our gaze to places like Europa, one of Jupiter's moons, we find an environment that closely resembles our underwater realms. Beneath its icy surface, scientists believe there exists a subsurface ocean kept warm by gravitational forces and heat generated from the moon's core. This ocean could be rich in the necessary chemicals and conditions to support life, analogous to Earth's deep-sea ecosystems, where organisms thrive around hydrothermal vents independent of sunlight. Similarly, Enceladus, a moon of Saturn, presents another fascinating comparison. This small celestial body ejects plumes of water and ice particles into space, suggesting an active ocean hidden beneath its frozen surface. These geysers offer tantalizing clues about the ocean underneath and hint at the possibility of microbial life, much like Earth's extreme environments. Beyond moons, when we consider Mars, we find the remnants of ancient oceans that once covered much of its surface. Though currently dry, the evidence of past water flow, river valleys, and lake beds shows a planet that has undergone drastic changes. Understanding these features helps scientists explore the potential for life that may have existed there, inviting comparisons with the historical evolution of Earth's own oceans. Asteroids and comets also hold clues to our understanding. Comets, for example, are often viewed as icy bodies containing water, and they may have delivered water to Earth itself during its formative years. This illustrates how water is not just restricted to the large bodies of water on Earth, but rather a common thread throughout the solar system. While our oceans are vibrant and full of life, they serve as a backdrop to compare with the vast and diverse environments found elsewhere in our solar system. From subsurface oceans on distant moons to ancient lakes on Mars, each of these environments gives us insight into the cosmic significance of water and the potential for life beyond our blue planet. The planet that is engulfed in intense radiation is Jupiter. In its atmosphere, formidable layers of radiation envelop the gigantic planet, primarily due to the ferocious magnetic field it possesses, which is more than 20 times stronger than that of Earth. This magnetic field captures charged particles from the solar wind, streams of energized particles emitted by the Sun, creating a chaotic dance within Jupiter's magnetic environment. As these particles spiral into the atmosphere, they collide with gases, leading to the creation of stunning auroras in the polar regions. These auroras are not merely beautiful displays, they are often much more powerful than those on Earth, driven by the planet's immense gravity and its dynamic atmosphere. The energy from these interactions can be so potent that the radiation emitted poses a significant threat to any spacecraft that dares to venture close to the planet. The intensity and complexity of the radiation and auroras on Jupiter highlight the planet's extreme environment, making it a fascinating subject for scientists studying planetary magnetism and atmospheric phenomena. The radiation environment in space poses significant challenges both for potential life and for human exploration. Beyond Earth's protective atmosphere and magnetic field lies an inhospitable realm filled with various types of radiation, including cosmic rays and solar radiation. This high-energy radiation can have damaging effects on living organisms by breaking molecular bonds and causing cellular damage, which can lead to illnesses such as cancer or genetic mutations. For any existing life forms, whether on distant planets or moons, the impact of radiation is profound. On worlds lacking a thick atmosphere or magnetic shield, like Mars, radiation can bombard the surface, creating a hostile environment. Thus, if life exists there, it would likely be hidden underground or in protected environments where this radiation can be minimized. For human explorers venturing beyond Earth, the radiation environment necessitates careful planning and protective measures. Long-duration missions to places like Mars will require habitats that can shield astronauts from harmful radiation while still allowing for activities outside those shelters. This might mean developing spacesuits and transportation systems that incorporate materials designed to absorb or deflect radiation. The radiation environment significantly influences both the potential for life elsewhere in the universe and the safety and feasibility of future human exploration. Understanding and addressing these radiation challenges will be crucial as we seek to uncover the mysteries of our solar system and beyond. Auroras are tremendous displays of light that occur in the polar regions of our planet, and their captivating visuals can be explained by a combination of scientific theories related to space weather and atmospheric science. The primary driver of these beautiful phenomena is the interaction between charged particles from the Sun and our atmosphere. When the Sun emits a stream of charged particles, known as solar wind, some of these particles venture towards Earth. The Earth is protected by a magnetic field that channels these particles toward the polar regions. Imagine this magnetic field as invisible lines that guide the incoming charged particles. As these particles descend into the atmosphere, they collide with gases like oxygen and nitrogen at high altitudes. These collisions transfer energy to the atmospheric gases, exciting the atoms and molecules in the process. Once the excited gases return to their normal states, they release that excess energy in the form of light, resulting in the mesmerizing displays of green, red, blue, and purple hues that we associate with auroras. Each color corresponds to the type of gas involved. For example, oxygen produces green and red tones, while nitrogen can create purples and blues. The position and movements of the auroras are also influenced by the Earth's magnetic field and solar activity levels. During peaks in solar activity, the Sun erupts with more charged particles, leading to more powerful and widespread auroras. This interaction between cosmic events and our atmosphere creates a dynamic display that continues to fascinate scientists and skywatchers alike, offering a blend of natural beauty and scientific wonder. The planet's magnetic field acts like a protective shield against harsh radiation from space, particularly charged particles emitted by the Sun. These particles, which flow constantly in what we call the solar wind, can be quite energetic and potentially harmful. However, when the solar wind encounters the magnetic field, it doesn't simply pass through. Instead, it interacts with the field in a dynamic way. As these charged particles approach the planet, they are steered by the magnetic field lines which flow from the magnetic poles. Most of this radiation is deflected away, but some particles can get caught in the magnetic field and spiral along these lines down toward the polar regions of the planet. Here's where it gets visually spectacular. As these high-energy particles plunge into the atmosphere, they collide with gas molecules, primarily oxygen and nitrogen, at high altitudes. This interaction transfers energy to the gas molecules, exciting them and causing them to emit light as they return to their normal state. This process creates the mesmerizing displays we know as auroras, with colors that vary from greens to reds and purples, depending on the type of gas and the altitude at which the collisions occur. Thus, the magnetic field doesn't just protect the planet, it transforms the potentially dangerous solar radiation into one of nature's most stunning spectacles. The dance of particles and light becomes a beautiful reminder of the interplay between the planet's defenses and the solar forces at work in our universe. Intense radiation in space poses significant health risks to both humans and technology. For astronauts, the most concerning effects of exposure to radiation include damage to DNA, which can lead to cancer. The radiation can also disrupt cellular processes, leading to issues such as radiation sickness, which manifests with symptoms like nausea, weakness, and skin burns, depending on the level of exposure. Beyond immediate health ramifications, long-term effects are also troubling. Astronauts may experience accelerated aging of tissues, leading to difficulties in eyesight and an increased risk of heart disease. Studies indicate that exposure to cosmic rays, which are high-energy particles from outside our solar system, can penetrate the body and affect organs differently, heightening the risk of developing cancers years after exposure. For technology, this radiation can wreak havoc on electronic components. Satellites and space instruments are vulnerable, as radiation can interfere with circuitry, potentially causing malfunctions or complete failures. This is particularly concerning for communication systems and navigation equipment. Engineers combat these issues by incorporating shielding and designing systems that can tolerate or recover from radiation effects. Yet these solutions cannot eliminate the risks entirely. The challenges posed by intense radiation in space necessitate careful planning and protective measures to safeguard both human health and the functionality of technology used in the exploration of our universe. The planet's auroras are not just beautiful displays of light. They are windows into the complex interactions between the planet's magnetic field and the solar wind, streams of charged particles released from the sun. By studying auroras, researchers can gain valuable insights into space weather phenomena and the behavior of radiation belts. When solar winds collide with the planet's magnetic field, they create disturbances that can lead to geomagnetic storms. These storms, characterized by fluctuations in magnetic energy, can energize particles in the upper atmosphere and cause them to spiral down along magnetic field lines, resulting in the stunning light shows of the auroras. Observing these phenomena helps scientists understand the dynamics of space weather, including how solar activity can affect the planet's environment and technology. Furthermore, auroras can indicate the strength and structure of radiation belts, the zones of charged particles trapped by the planet's magnetic field. By examining how different solar conditions influence the intensity and location of auroras, researchers can better predict the behavior of these radiation belts. This understanding is crucial because fluctuations in space weather can have serious implications for satellite operations, communications, and even power grids on Earth. The study of auroras not only reveals the beauty of nature, but also enhances our knowledge of the underlying processes that govern space weather events and their potential impacts on our planet. This field of research is vital for advancing our ability to forecast and mitigate the effects of solar storms on human activities and technology. Observing a planet from a safe distance presents a series of fascinating technical challenges that researchers and engineers must overcome. First and foremost, the sheer distances involved in space make it difficult to obtain clear images and data. As observatories and spacecraft venture farther away from Earth, the faintness of signals becomes a significant hurdle. Just as a distant sound can become difficult to hear, light and other forms of electromagnetic radiation weaken over vast stretches, leading to the need for highly sensitive instruments. Another challenge involves the limitations of the instruments used to gather and analyze data. Telescopes, whether grounded on Earth or placed in orbit, rely on precise optics and advanced technologies to focus light and filter out background noise, which can obscure the target planet. Each planet has its own unique atmospheric composition, brightness, and even physical characteristics. Designing equipment that can adapt to these variables is essential for accurate observations. The effects of atmospheric interference, such as turbulence and weather conditions, also complicate ground-based observations. Waves of air can distort the light from celestial objects, causing them to appear blurry. This necessitates the use of adaptive optics technology, which involves adjusting the telescope in real time to correct for these disturbances. In addition to hardware limitations, there's the concept of the radio signal delay. Data transmitted from distant planets or spacecraft can take an appreciable amount of time to travel back to Earth. When combined with the need for real-time data analysis, this can hinder mission objectives, making it necessary to develop strategies for predictive modeling and autonomous decision-making in various missions. Lastly, navigating extreme environments is another concern. Spacecraft encountering situations such as high radiation zones, extreme temperatures, and the vacuum of space must be built from materials that can withstand these harsh conditions. These robust designs often increase costs and complicate the engineering process, requiring innovative solutions to maintain functionality over long durations. Observing planets from a distance encompasses challenges related to distance, instrument sensitivity, atmospheric interference, communication delays, and the extreme conditions of space. Each obstacle demands inventive engineering and a deep understanding of the principles of physics and astronomy, making space observation both complex and thrilling. Auroras, those spectacular displays of light swirling across the polar skies, have not only captivated observers with their beauty, but have also sparked imaginations throughout history. Ancient peoples, observing these shimmering lights, often felt compelled to explain their appearance. The eerie glow was sometimes viewed as a bridge to other realms, a signal from the gods, or even the spirits of ancestors communicating with the living. These interpretations could easily birth cautionary tales about heedfulness in the face of nature's wonders, reminders that while these celestial phenomena are awe-inspiring, they can also symbolize turbulence or significant change. In various cultures, auroras might be woven into legends that caution against trespassing into sacred spaces or misusing nature's gifts, perhaps suggesting that those who disrespect the earth could invoke the wrath of the spirits behind these glowing skies. Additionally, tales might portray auroras as omens, heralding significant events, perhaps a warning of conflict or upheaval, teaching communities to pay attention to signs beyond their immediate understanding. As these narratives pass down through generations, they crystallize the idea that human action is intertwined with the broader universe. The night sky, filled with brilliant lights, serve not just as a display of cosmic wonder, but as a powerful metaphor. Engaging with the forces of nature requires respect and awareness. Thus, auroras have shaped folklore and wisdom across cultures, connecting humanity's existence to the majestic dance of forces that govern our world, reminding us always to tread thoughtfully amidst the wonders of the universe. The planet, bathed in radiation, draws intriguing parallels with several known cosmic phenomena. First, we can look to the characteristics of neutron stars, particularly those that emit intense beams of radiation known as pulsars. These stellar remnants result from supernova explosions and possess incredibly compact yet dense structures. As they spin, their powerful gravitational fields and rapid rotation create beams of electromagnetic radiation that sweep across space, much like a lighthouse. A planet inside a radiation-rich environment would experience similar intense exposure to such energetic particles, affecting its atmosphere and surface. Another compelling comparison can be made with the environment surrounding supermassive black holes, particularly in active galactic nuclei. These regions are known to emit high levels of radiation due to the accretion of matter being pulled in by the black hole's immense gravity. The resulting interactions and energy releases can create intense radiation belts, akin to what might be experienced by a planet orbiting in close proximity to such a force. The radiation not only influences the immediate environment, but can also lead to extreme temperatures and potentially sterilize surfaces, rendering any form of life highly unlikely. Lastly, we can draw a connection to the harsh conditions found on planets like Jupiter, specifically in its radiation belts. The intense magnetic field of Jupiter traps charged particles, creating zones of concentrated radiation. For any moon or surrounding environment, this radiation poses significant challenges, similar to what a planet near a radiation-bathed star would face. By examining these parallels, we see that while the specifics of radiation environments may differ, the profound effects they impose on planetary atmospheres and potential habitability share common themes across the cosmos. These interconnected phenomena serve as a reminder of the extremes that exist beyond our own planet and the varied conditions that can arise from the universe's most energetic events. The discovery and study of extreme planets, particularly those found in inhospitable environments, greatly enhance our understanding of planetary systems and the diverse conditions they can endure. Picture a planet that exists in a dizzyingly close orbit around its star, where temperatures soar to levels that would incinerate most materials on Earth. These findings compel scientists to rethink the possibilities of planetary formation and survival. Observing these extreme conditions reveals how atmospheric chemistry can differ wildly from what we know. For instance, planets with thick, scorching atmospheres often feature elements and compounds that behave differently due to extraordinary heat and pressure, creating clouds of minerals or smog-like layers that obscure our view. Studying these atmospheres helps us understand how energy from the star interacts with the planet, leading to processes that may even allow for exotic weather patterns completely alien to our experiences. Furthermore, the discovery of planets with extreme gravitational forces also contributes to our knowledge of how these environments affect potential habitability. With gravity's role in shaping a planet's atmosphere and weather systems, scientists can analyze the structural integrity of a planet under such stresses, helping to theorize about the potential for life, or, at the very least, the materials necessary for life as we understand it. By examining these extreme planets, astronomers can refine models of planet formation and the conditions necessary for a planet's development. Each discovery serves as a new key to unlock further mysteries of planetary evolution and compatibility with the notion of life. They act as laboratories for testing theories that could eventually help us grasp the full spectrum of planetary diversity beyond our solar system. These findings underscore not just how unusual planets can be, but also how adaptable our definitions of habitability might need to become as we continue to explore the cosmos.